There's something hauntingly beautiful about the way the universe keeps its most incredible secrets just out of reach, like whispers from the edge of existence. If you could tune your ears to the cosmos, you might hear the faint, rhythmic pulses of neutron stars, the densest objects in existence aside from black holes. These celestial remnants are so bizarre, a single teaspoon of their material would weigh 1 billion tons on Earth. But what if I told you some of these cosmic lighthouses are so far away, their light takes millions of years just to reach us? Today, we're setting off on a journey to the farthest edges of the known universe to uncover 50 mind-bending facts about the most distant neutron stars, objects so extreme they defy everything we think we know about physics. Imagine a star so massive it collapses under its own weight, crushing atoms into a sea of pure neutrons. Now, picture that star spinning faster than a kitchen blender, hurling beams of radiation across the cosmos like a lighthouse cutting through the dark. These are neutron stars, and some of them are so distant, their signals are barely whispers by the time they reach Earth. Yet, in those whispers, scientists have found clues about the birth of the universe, the nature of gravity, and even the fabric of space-time itself. What makes these far-flung neutron stars so special? Why do they challenge our understanding of physics in ways nothing else can? This isn't just a story about distant objects in space. It's a tale of human curiosity and the relentless pursuit of knowledge. We'll explore how astronomers detect these ultra-distant neutron stars, the strange phenomena they exhibit, and what they reveal about the universe's most violent events. From starquakes that ripple across their surfaces to magnetic fields strong enough to rip atoms apart, these cosmic oddities are rewriting the rules of astrophysics. So, if you're ready to dive into the mysteries lurking at the edge of the observable universe, stick around, because what we're about to uncover will leave you in awe of just how strange and wondrous the cosmos truly is. To understand why neutron stars are some of the most extreme objects in the universe, we have to start with their violent birth. Picture a massive star much larger than our Sun, reaching the end of its life. After burning through its nuclear fuel, it can no longer withstand its own gravity. In a cataclysmic explosion called a supernova, the star's outer layers are blasted into space while its core collapses inward at unimaginable speeds. What's left isn't just a dense remnant, it's a city-sized sphere where matter has been compressed beyond recognition. The physics here defies intuition. Under this intense gravitational squeeze, electrons and protons inside atoms are forced together, merging into neutrons. The result, a neutron star, a celestial object so dense it packs 1.5 times the mass of our Sun into a space no wider than Manhattan. If you could scoop up just a teaspoon of this material, it would weigh around 1 billion tons on Earth. That's like crushing Mount Everest into a sugar cube. But here's where things get even stranger. Neutron stars aren't just dense, they're cosmic laboratories where the laws of physics are pushed to their limits. Their surfaces are smoother than a perfect marble, yet their gravity is so strong it bends light into a halo around them. Some spin hundreds of times per second, their magnetic fields powerful enough to strip electrons from atoms thousands of miles away. These extreme conditions let scientists study matter in ways impossible on Earth, offering clues about how particles behave under pressures we can't replicate in any lab. What makes them truly special, though, is how they challenge our understanding of reality. Inside a neutron star, matter may exist in states we've never seen, perhaps even breaking down into quarks, the fundamental building blocks of protons and neutrons. Some theories suggest they might contain exotic particles we haven't discovered yet, or even tiny pockets of strange matter that could rewrite the rules of physics. Every distant neutron star we detect is like a message in a bottle, carrying secrets from the far reaches of space, and the deeper we look, the more we realize how much we still have to learn. The story of how neutron stars were discovered reads like a cosmic detective novel, one that began with a mystery so puzzling, scientists briefly wondered if they'd stumbled upon signals from intelligent life. It was 1967 when a young graduate student named Jocelyn Bell Burnell noticed something peculiar in the data from a radio telescope she'd helped build. The telescope was designed to study distant galaxies, but what caught her attention was a series of sharp, regular pulses arriving every 1.337 seconds with uncanny precision. At first, no one could explain these rhythmic bursts. The signals were so consistent, so artificial in their timing, that researchers jokingly labeled them LGM, short for Little Green Men. But Burnell's persistence unraveled the truth. These weren't alien broadcasts, they were the heartbeat of a rapidly spinning neutron star, later named a pulsar. As the star rotates, its powerful magnetic field channels radiation into narrow beams that sweep across space like a lighthouse. When those beams happen to point toward Earth, we detect them as pulses. This discovery didn't just reveal a new type of celestial object, it opened a window into some of the most extreme physics in the universe. What makes this breakthrough even more remarkable is how close we came to missing it entirely. The telescope's original purpose was to study quasars, and the equipment was barely sensitive enough to catch those faint pulses. Burnell had to meticulously analyze miles of paper chart recordings by hand, spotting patterns others might have dismissed as interference. Her sharp eyes and determination changed astronomy forever. The first confirmed pulsar, now known as CP-1967, spins so fast that its surface moves at nearly 15% the speed of light. That initial discovery shattered assumptions about what could exist in the cosmos, proving that stars could collapse into objects far stranger than anyone had imagined. Today, we know pulsars are neutron stars in disguise, their precise ticks serving as cosmic clocks that help us test Einstein's theory of relativity and even map gravitational waves. Jocelyn Bell Burnell's story reminds us that the universe often hides its greatest wonders in the details, waiting for someone curious enough to look closer. Those first puzzling pulses weren't just a scientific breakthrough, they were a lesson in how much we still have to learn about the cosmos, and the most incredible part. 5 decades later, we're still deciphering the secrets these spinning stellar corpses have to tell us. If you thought neutron stars couldn't get any stranger, meet PSRJ-1 7482446 AD, the fastest spinning neutron star ever discovered. Clocking in at 716 revolutions every single second, this cosmic speed demon rotates so fast its surface moves at nearly a quarter the speed of light. To put that insanity into perspective, imagine a blender spinning so violently it should tear itself to shreds, except here, the neutron star's immense gravity, billions of times stronger than Earth's, holds it together like an unbreakable cosmic glue. This dizzying spin creates conditions so extreme they bend the rules of physics. At that speed, the star's equator is stretching outward, barely restrained by gravity, while a single millisecond of its rotation would see you flung into space with enough force to vaporize you instantly. What's even more astonishing is that this isn't some newborn star fresh from a supernova. It's been spinning at this breakneck pace for thousands, possibly millions of years without slowing down. Scientists believe this extreme rotation comes from a cosmic theft. The neutron star likely stole gas from a neighboring star, funneling it onto its surface in a process called accretion. As this stolen matter crashed onto the star, it transferred energy like a cosmic push on a merry-go-round, speeding it up to these impossible velocities. And unlike a blender that would eventually overheat and fail, PSRJ-1 7482446 AD keeps spinning relentlessly, its magnetic field and gravity locked in a perfect, unshakable balance. But here's the real brain twister. If this star spun just a little faster, it would reach a point where gravity could no longer contain it. the equator would fly apart and the neutron star would cease to exist, crossing a threshold we still don't fully understand. That makes this pulsar not just a curiosity, but a critical test of how matter behaves under the most extreme forces the universe can muster. Every pulse it sends our way is a reminder of just how bizarre and how breathtaking the cosmos can be. Think about touching a stove burner. Now imagine something so hot, it makes that feel like an ice cube. Newborn neutron stars are born in the fires of supernova with surface temperatures soaring past 1 million degrees Kelvin. That's hotter than the core of most stars, and it's only the beginning of their story. In their first moments, these stellar remnants blaze with the heat of their violent birth, glowing fiercely across the electromagnetic spectrum. But unlike a campfire that fades in hours, neutron stars cool over millennia, their surfaces slowly dimming as they radiate energy into the void. Even after tens of thousands of years, some still retain temperatures rivaling the sun's surface around 5,000 degrees. Spotting this fading glow isn't easy, though. Without the raging inferno of a star's fusion to keep them bright, neutron stars are often detected only by their faint infrared signatures, like embers in cosmic darkness. Infrared telescopes like NASA Spitzer and the James Webb Space Telescope have become essential tools for studying these cooling giants. By capturing the subtle heat radiating from their surfaces, astronomers can piece together their life stories, like reading the cooling timeline of a forge left by a blacksmith. Some neutron stars, wrapped in ultra-dense atmospheres of carbon or oxygen, cool unevenly, creating hotspots near their magnetic poles that flicker like cosmic lighthouses. Others, stripped bare by their own gravity, reveal surfaces so smooth and uniform, their heat bleeds away like ink in water. What's truly fascinating is how these temperatures reveal the star's deepest secrets. The rate at which a neutron star cools can hint at the exotic physics happening beneath its crust, whether it's filled with superfluid neutrons, strange quarks, or particles we haven't even named yet. Every degree dropped is a clue, a whisper from an object that defies the ordinary. And as we peer deeper into the infrared, who knows what other mysteries these fading giants will unveil. Among these cosmic oddities, magnetars stand in a category all their own, neutron stars turned up to 11. Picture a magnetic field so powerful, it twists the very fabric of reality. These objects wield forces quadrillions of times stronger than Earth's humble magnetism, making them the universe's ultimate magnetic monsters. A magnetar's grip is so intense, it could distort the electron clouds of atoms from hundreds of thousands of miles away. If one were to magically appear halfway between Earth and the Moon, its magnetic field would be strong enough to scramble every credit card on our planet, not by hacking, but by physically altering the magnetic strips. That's not science fiction, it's the raw, unsettling power of physics pushed to its breaking point, but the true terror of magnetars lies in their tantrums. Occasionally, these stars release bursts of energy so violent, they outshine our entire galaxy for a fraction of a second. These gamma-ray flares happen when the star's crust, under unimaginable magnetic stress, finally snaps like an over-tightened guitar string. The resulting starquake unleashes enough energy to boil oceans, vaporize atmospheres, and rewrite the rules of what we thought was possible. One such flare, detected in 2004 from 50,000 light-years away, still managed to disrupt Earth's upper atmosphere and temporarily blind satellites. What makes magnetars even more baffling is how rare they are. Of the roughly 3,000 known neutron stars, only about 30 have been confirmed as magnetars. Their magnetic fields decay relatively quickly, leaving behind quieter neutron stars, meaning we're catching them in a fleeting, hyper-violent phase of their lives. Yet for all their destructive potential, magnetars are also cosmic gold mines for scientists. Their extreme conditions serve as natural laboratories for testing quantum electrodynamics, the behavior of matter in absurd magnetic fields, and even the nature of spacetime itself. Every flicker, every flare is a message, a reminder that the universe isn't just stranger than we imagine, but stranger than we can imagine. Some neutron stars don't just spin quietly in the void, they devour. Meet PSRB 1957+20, nicknamed the Black Widow Pulsar, a cosmic predator that's systematically destroying its stellar companion. This isn't some slow orbital dance between equals. It's a one-sided massacre playing out across light years, where the pulsar's lethal radiation is slowly boiling away its partner star like water evaporating from a pot left on high heat. The violence starts with the pulsar's rotation. Spinning 622 times per second, it whips its magnetic fields through space at nearly a fifth the speed of light. These fields accelerate particles to near light speeds, creating a hurricane of high-energy radiation that never lets up. Every second, this deadly pulsar bombards its companion, a lightweight star only a fraction of our Sun's mass, with enough X-rays and gamma rays to strip away its atmosphere atom by atom. What's left behind is a ghostly trail of ionized gas, stretching through space like the wake of a ship. Telescopes have captured this eerie debris field glowing faintly in optical and X-ray light, a cosmic crime scene marking where the star's material was blasted into oblivion. The companion, now just a scorched remnant, still orbits the pulsar every 9 hours, trapped in a death spiral that will eventually leave it completely disintegrated. Scientists call this process ablation, but that clinical term hardly captures the brutality. The pulsar's radiation doesn't just erode the star, it warps the very physics of the system. The escaping gas forms a shock wave ahead of the star as it plows through space, while intense pressure from the pulsar's wind creates a comet-like tail of stripped particles stretching thousands of miles. Black Widow's behavior gives astronomers a front-row seat to stellar destruction on an epic timescale. Eventually, the companion star will be reduced to a planetary mass cinder, or perhaps vanish entirely, leaving the pulsar alone once more. Until then, this lethal dance continues, a reminder that even in the vastness of space, some relationships are anything but harmonious. Even the crust of a neutron star isn't immune to cracking under pressure, literally. Imagine a layer of material 10 billion times stronger than steel, forged under the most extreme gravity imaginable. Now picture that surface suddenly fracturing like thin ice underfoot. These aren't just cracks, they're starquakes, seismic events so violent they'd register as magnitude 32 earthquakes if they happened on Earth. That's not a typo. A quake that powerful would release more energy than every volcanic eruption, earthquake, and nuclear explosion in human history combined, except here, it's confined to an object barely 12 miles wide. These cosmic tremors happen when the neutron star's crust, a crystal lattice of iron nuclei packed impossibly tight, finally succumbs to the strain. The star's insane rotation and ludicrously powerful magnetic field twist this crust like taffy over time. Eventually, something has to give. When it does, the entire surface lurches in what scientists call a glitch, a sudden adjustment in rotation speed. But the real fireworks come from the energy released in that split-second snap. The crust shudders, creating ripples that propagate across the surface at near light speed, unleashing bursts of X-rays so bright they outshine entire galaxies for milliseconds. NASA Chandra X-ray Observatory has caught these explosions in action, capturing flares that spike and fade in less time than it takes to blink. What makes these events so fascinating isn't just their scale, it's what they reveal about the star's interior. Like geologists studying earthquakes to map Earth's core, astrophysicists use these X-ray bursts to probe the hidden layers beneath the crust. Some theorize the quakes expose patches of superfluid neutrons swirling beneath, while others suggest they might even trigger the Magnetars' deadly gamma-ray flares. But here's the kicker: the aftermath of a starquake can leave the neutron star permanently scarred. The crust's fractures might heal over centuries, but the magnetic field lines anchored to the surface snap and reconnect in the process, unleashing secondary bursts of radiation. It's a chain reaction of cosmic violence, a reminder that even in the cold depths of space, nothing stays perfectly still. Every crack, every glitch is a clue, another piece of the puzzle in understanding how matter behaves when pushed to the absolute edge of existence. 5.5 billion light-years from Earth, buried in the afterglow of one of the universe's most violent explosions, lies a neutron star so distant it defies belief. Designated JRB 200522A, this cosmic beacon announced itself with a gamma-ray burst so powerful, it briefly outshone every star in its host galaxy combined. What makes this object extraordinary isn't just its mind-numbing distance, it's that we detected it at all. Gamma-ray bursts like this one typically signal the birth of a black hole, but Hubble's keen eye caught something unexpected. Nestled in the fading embers of the explosion was a peculiar infrared glow, a fingerprint matching no known phenomenon except one, a newborn neutron star. The odds were staggering. For a neutron star's light to reach us from such an unfathomable distance, its jet had to punch through intergalactic space for longer than our solar system has existed. That it remained visible at all is a testament to the raw energy unleashed in its creation. Detecting objects this remote pushes telescopes to their limits. At 5.5 billion light-years, the light from JRB 200522 began its journey when Earth was just a molten rock, before multicellular life existed, before the continents took their modern shapes. By the time those photons reached Hubble's mirror, they'd been stretched and dimmed by the expanding universe, their signals diluted to near nothingness. Spotting them required perfect timing. Hubble had to swing into action within days of the burst, capturing the afterglow before it vanished into the cosmic background. Yet the real challenge wasn't just distance, it was distinguishing the neutron star's signal from the chaos around it. Gamma-ray bursts are messy affairs, often shrouded in debris and competing light sources. What clinched the discovery was the infrared signature, a telltale bump in the data that matched models of a young neutron star's magnetic fury. Without that precise spectral clue, this record-breaking object might have slipped through our fingers entirely. What JRB 200522 reveals is both humbling and exhilarating. Its existence suggests neutron stars can form in conditions we once thought reserved for black holes, challenging our models of stellar death. And if Hubble could spot one at the edge of the observable universe, who knows how many more are out there waiting for the right moment, the right telescope, and the right curious minds to uncover them. Neutron stars and black holes might seem like cosmic siblings, both born from the death throes of massive stars, but their differences reveal the knife's edge between reality and oblivion. Picture a collapsing star as a cosmic balancing act. As the core implodes, gravity fights a brutal tug of war with quantum forces. For neutron stars, that battle ends in a stalemate. The core crushes down until neutrons resist further collapse, creating an object so dense it warps space without fully devouring it. Black holes, they're what happens when gravity wins outright, crushing matter past the point of no return. The numbers tell a chilling story. A neutron star packs 1 to 3 solar masses into a sphere no wider than a city, but push that mass beyond roughly 2.2 times the sun's weight, and even neutrons can't hold the line. The core keeps collapsing until it forms a singularity, a point of infinite density where the laws of physics as we know them cease to apply. That critical threshold, known as the Tolman-Oppenheimer-Volkoff limit, is the universe's way of drawing a line between the bizarre and the incomprehensible. Observing these objects couldn't be more different. Neutron stars announce themselves with pulsating beams of radiation, their magnetic fields lighting up the cosmos like interstellar lighthouses. Black holes, they're the ultimate introverts. No light escapes their event horizons, so we detect them indirectly, by the way they bend space-time or the screams of gas torn apart as it spirals into the void. Some neutron stars, like the infamous PSRJ 034, 8+0432, even orbit black holes, offering scientists a front-row seat to compare their behavior side by side. Yet the most astonishing difference lies beneath the surface. Dive into a neutron star and you'll find layers of hyper-compressed matter, a crust of iron nuclei, a mantle of free-flowing neutrons, and possibly a core of exotic quarks. A black hole hides no such structure. Beyond its event horizon, matter isn't just crushed, it's erased from the universe's ledger, leaving behind only mass, spin, and charge. It's the difference between a vault and a shredder. This cosmic dichotomy raises a haunting question. What happens in those final moments when a neutron star teeters on the brink of becoming a black hole? Simulations suggest the star might oscillate wildly, briefly forming a quark star before succumbing to gravity's grip. Others theorize it could trigger a secondary explosion, a last gasp before vanishing forever. For now, these edge-of-reality transformations remain one of astrophysics' greatest mysteries, hiding clues about how the universe draws the line between existence and oblivion. The haunting rhythm of a neutron star isn't just something astronomers see, it's something they hear. By converting the rapid-fire pulses of a pulsar's radio emissions into sound waves, scientists have turned these cosmic lighthouses into interstellar drummers, beating out a cadence that's as precise as it is eerie. Take PSRB 0329+54, for example. This pulsar's radio waves, when translated into audio, produce a sharp, metallic click every 0.714 seconds, a sound so regular it could pass for a metronome set by the universe itself. The process of turning starlight into sound is simpler than you might think. Radio telescopes capture the pulsar signals as waves of energy, which are then converted into electrical impulses. Those impulses feed into a speaker where they become audible clicks or tones. The result, a stark, rhythmic pattern that feels almost mechanical, like a giant cosmic clock ticking away in the void. Some pulsars, spinning hundreds of times per second, produce rapid staccato beats, while slower ones evoke the deep, resonant tolling of a bell. But these sounds aren't just for show, they're a goldmine for researchers. Slight variations in the rhythm can reveal hidden details about the star's rotation, magnetic field, or even unseen companions orbiting nearby. When the pulses speed up or slow down unexpectedly, it might mean the star's crust has cracked in a starquake, or that it's being tugged by the gravity of a passing asteroid. In rare cases, astronomers have even detected echoes in the signal, ghostly repetitions caused by the pulsar's beams bouncing off interstellar debris. What's truly chilling, though, is how these sounds bridge the gap between the cosmic and the familiar. The steady beat of a pulsar could easily be mistaken for the hum of machinery or the tapping of Morse code, a reminder that the universe speaks in rhythms we're only beginning to decode. Listening to these celestial timekeepers, you can't help but wonder, if the stars are singing, what else might they be trying to tell us? In the darkness of space, two neutron stars pirouette toward catastrophe, each a city-sized mass packing more weight than our sun. When they finally collide, it's not just a merger, it's a cosmic alchemy lab forging precious metals in quantities impossible anywhere else. Take the event known as GW 170817, detected in August 2017. For the first time in history, astronomers witnessed the aftermath of such a collision through both gravitational waves and a blinding gamma-ray burst, a one-two punch of discovery that changed how we understand the universe's heaviest elements. The violence of this kilonova was staggering. As the stars spiraled inward at a third the speed of light, their crushing gravity ripped them apart, spraying neutron-rich material into space like a cosmic fountain. In that maelstrom, neutrons bombarded atomic nuclei at unimaginable rates, building heavier and heavier elements through a process called rapid neutron capture. Within seconds, this stellar crucible forged hundreds of Earth masses worth of gold, platinum, and other rare metals, enough to lasso every piece of jewelry on our planet 1,000,000 times over. What made GW170817 truly groundbreaking was how we detected it. The Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the ripples in space-time as the stars merged, while NASA Fermi telescopes simultaneously recorded the gamma-ray burst. This dual signature allowed scientists to pinpoint the event's location, a galaxy called NGC 4993, 130 million light-years away, and train telescopes on the aftermath. What they saw defied expectations, a rapidly fading glow that started blue, then shifted to red as heavier elements formed in the expanding debris cloud. The aftermath revealed something even more profound. For decades, astronomers debated where half the universe's gold, platinum, and uranium originated. Supernova couldn't explain the abundance, but kilonovas like this one could. Every gold ring on Earth, every platinum catalytic converter in a car, might owe its existence to neutron star collisions that happened billions of years before our solar system formed. Yet the real wonder lies in how fleeting these events are. A kilonova's brilliance lasts barely a week before fading into obscurity, its precious cargo scattered across interstellar space. That means catching one in action requires perfect timing, and GW170817 was our first glimpse into a process that's been shaping the chemistry of the cosmos since the dawn of time. Who knows what other secrets these cosmic gold factories are hiding? The beams slicing through space from a pulsar don't just radiate randomly. They're sculpted by one of the most extreme magnetic environments in existence, creating what astronomers call the lighthouse effect. Picture this: a neutron star's magnetic axis isn't lined up with its rotational axis. Instead, it's tilted like a wobbling top with a spotlight glued to its side. As the star spins, those magnetic poles whip around, channeling radiation into twin cones that shoot outward like cosmic searchlights. Here's where the magic happens. Those beams aren't visible in all directions, they're tightly focused, which means we only detect pulses when one sweeps across Earth's line of sight. It's like standing in a dark field watching a distant lighthouse. You don't see its light continuously, just a flash each time the beam swings toward you. For pulsars, that flash can arrive with metronomic precision, some ticking every few milliseconds, others every few seconds, depending on how fast the star is spinning. The three-dimensional geometry of this dance is crucial. If the magnetic and rotational axes were perfectly aligned, we'd see no pulses at all, just a steady glow. It's the misalignment that makes pulsars blink. Some, like the Crab pulsar, have their magnetic poles nearly perpendicular to their spin axis, creating sharp, bright pulses. Others, with shallower tilts, produce gentler, broader flashes, but the lighthouse analogy only goes so far. Unlike a human-made beacon, a pulsar's beams aren't made of visible light. They're often bursts of radio waves, X-rays, or even gamma rays, accelerated to near light speed by the star's monstrous magnetic field. And the energy isn't gentle. A single sweep can carry enough power to outshine the sun for that split second. What's even wilder, sometimes pulsars flip. Over centuries, the magnetic axis can slowly realign, causing the beams to drift, or even vanish from our view entirely. It's a reminder that these cosmic lighthouses aren't static. They're dynamic, evolving monsters, and every pulse we catch is a fleeting snapshot of their relentless spin. The precision of neutron stars isn't just impressive, it's almost supernatural. Some pulsars, like PSRJ 437+1715, spin with such clockwork regularity that they lose just 1 second every 300 million years. That's a level of stability that puts Earth's most advanced atomic clocks to shame. These celestial metronomes owe their accuracy to sheer mass. Their incredible density makes them nearly immune to the external forces that might nudge a lighter object off rhythm. Consider the atomic clocks that govern modern technology. Their precision relies on the vibration of cesium atoms, but even these marvels can drift by microseconds over decades. A pulsar, by contrast, is a gravitational gyroscope, its rotation locked in by the inertia of a star's worth of matter compressed into a sphere barely wider than Manhattan. The fastest, called millisecond pulsars, spin hundreds of times per second with variations so tiny they're measurable only after years of observation. This reliability has scientists dreaming big. NASA's Neutron Star Interior Composition Explorer, or NISA, experiment aboard the International Space Station has already tested using pulsar signals for navigation. The idea, by tracking the arrival times of pulses from multiple neutron stars, each acting like a cosmic lighthouse, a spacecraft could triangulate its position anywhere in the galaxy, no GPS satellites required. It's a concept straight out of science fiction, except the math checks out. The key lies in pulsar timing arrays. Just as GPS relies on signals from multiple satellites, spacecraft of the future might lock onto the rhythmic pulses of neutron stars like PSRB 1937+21, whose ticks arrive with nanosecond predictability. The European Space Agency's Pulsar initiative even mapped out how a probe could use these signals to navigate interstellar space, autonomously vital for missions where real-time communication with Earth is impossible due to light-year delays. But beyond engineering, these cosmic clocks are reshaping fundamental physics. Tiny irregularities in pulse timing have revealed hidden exoplanets, tested Einstein's general relativity under extreme gravity, and even provided evidence for gravitational waves. Each tick is a message, a ripple in space-time carrying secrets about the universe's most violent collisions and the invisible forces bending reality itself. The stars, it seems, are keeping time better than we ever could, and if we listen closely, they might just guide us to the frontiers we've only dreamed of reaching. Imagine a cosmic Russian nesting doll, a neutron star wrapped inside the bloated atmosphere of a red giant. This isn't science fiction. It's the Thorne-Zitkow object, one of the most bizarre theoretical hybrids in astrophysics. Named after physicists Kip Thorne and Anna Zitkow, who first proposed the idea in 1975, this hypothetical monster would form when a neutron star gets swallowed by its massive companion star. Instead of being torn apart, the neutron star sinks to the red giant's core, where it orbits like a dark, dense parasite feeding on the star's material while utterly transforming it from within. The physics here is mind-bending. A red giant's core is already a chaotic place, with nuclear fusion churning out energy as the star nears the end of its life. But drop a neutron star into that environment and everything changes. The neutron star's gravity would disrupt the red giant's internal dynamics, creating a swirling maelstrom of gas around it. Over time, the neutron star might accrete so much material that it triggers exotic nuclear reactions rarely seen elsewhere in the universe, producing elements like rubidium, lithium, and molybdenum in unusual abundances. Spotting a Thorne-Zitkow object, though, is like searching for a needle in a galaxy-sized haystack. The few potential candidates identified, like HV 2001-12 in the Small Magellanic Cloud, show chemical signatures that don't match typical red giants. Their atmospheres contain too much rubidium and too little iron, hinting at something strange happening deep inside, but confirming these objects is fiendishly difficult. The neutron star's presence would only subtly alter the outer layers of the red giant, making its fingerprints easy to miss in telescope data. The hunt hinges on spectroscopy analyzing starlight for telltale chemical clues. Even then, alternative explanations exist. Some of these oddball stars might just be chemically peculiar giants with unusual internal mixing. To prove a Thorn-Zitkow object exists, astronomers need to catch one in the act of behaving unlike any normal star, perhaps by detecting X-ray emissions from the neutron star's surface or spotting the gravitational wobble it induces in its host. What's at stake isn't just adding another oddity to the cosmic zoo. If confirmed, Thorn-Zitkow objects would reveal a previously hidden chapter in stellar evolution, one where neutron stars rewrite the rules of how stars live and die. They might even explain why some regions of space are sprinkled with rare elements that shouldn't exist there. For now, these cosmic chimeras remain tantalizingly out of reach, daring us to look closer and question what else might be hiding in plain sight. The surface of a neutron star might seem like a place where nothing could survive, and yet, these cosmic dead stars manage to cling to something resembling an atmosphere. Picture a layer of gas so thin it would make Earth's exosphere look dense by comparison. These wispy envelopes, likely made of hydrogen or carbon, cling to the star's surface with barely any thickness at all, sometimes just a few inches deep. But don't let their fragility fool you. Even this whisper-thin veil holds clues about the star's history, its magnetic fury, and the unfathomable forces at work just beneath it. X-ray telescopes like NASA Chandra and ESA's XMM Newton have become the ultimate tools for studying these ghostly atmospheres. Because neutron stars radiate so intensely in X-rays, their atmospheric fingerprints appear as subtle dips and peaks in the high-energy light they emit. Imagine holding a prism up to a spotlight, except here, the prism is the neutron star's atmosphere, and the light it bends reveals which elements are present. Hydrogen, for instance, absorbs X-rays at very specific energies, leaving telltale gaps in the spectrum. Carbon does the same, but at different wavelengths. Catching these signatures requires instruments so sensitive they can distinguish between photons with energies differing by less than 1%. What's truly staggering is the contrast between this delicate outer layer and the nightmare of density beneath it. Just below the atmosphere, the neutron star's crust begins, a crystalline lattice of iron nuclei packed so tightly, a single sugar cube-sized chunk would weigh billions of tons on Earth. The transition from atmosphere to crust happens in a span shorter than a city block, yet the conditions change as drastically as jumping from the vacuum of space into the heart of a nuclear explosion. Some neutron stars, like the one at the center of the Cassiopeia, a supernova remnant, even show evidence of polarized X-rays, hinting that their magnetic fields are so strong they've stretched atoms into needle-like shapes within the atmosphere. Others, like RxJ 18565.5375, appear to have no atmosphere at all, their surfaces so smooth and bare that X-rays reflect off them like sunlight on polished chrome. But perhaps the most fascinating detail is how these atmospheres form in the first place. After the trauma of a supernova, lingering traces of the original star's outer layers might rain back down onto the neutron star, creating a transient shroud. Alternatively, gas stolen from a companion star could accumulate over millennia. Either way, these fragile skins are cosmic archaeology, hiding the history of the star's violent birth and the turbulent environment it calls home. And here's the kicker: these wispy layers might be the only part of a neutron star we can ever directly study. Beneath them, matter is so compressed that light can't escape, meaning the atmosphere is our only window into understanding what lies below. Every flicker, every spectral line is a breadcrumb leading us deeper into the mystery of how matter behaves when pushed beyond any limit we can recreate on Earth. In a universe where neutron stars often spin faster than blender blades, PSRJ 0250 plus 5854 stands out like a cosmic tortoise. Clocking in at a leisurely 23.5 seconds per rotation, this pulsar defies everything we know about how these objects should behave. Most newborn neutron stars spin dozens of times per second, slowing gradually over millennia as their magnetic fields break the rotation. but this sluggish outlier shouldn't even exist, at least not according to textbook spin-down theories. The mystery lies in the numbers. Based on its rotation speed and estimated age, this pulsar's magnetic field should be hundreds of times stronger than observed. Normally, that magnetic drag is what slows pulsars down over time, like a spinning top sinking into molasses, yet PSRJ 0250 plus 5854 refuses to follow the script. Its magnetic field measures surprisingly weak, meaning there's no clear explanation for why it's spinning so slowly. Either this star formed with an unusually lazy rotation, something current models say is nearly impossible, or some unseen factor is tampering with its spin-down rate. One leading theory suggests hidden complexities in the star's interior might be at play. Superfluid neutrons swirling beneath the crust could periodically transfer angular momentum outward, giving the star brief speed boosts that mask its true age. Alternatively, its magnetic field might be tangled in ways we can't detect from Earth, creating pockets of resistance that break the star erratically. Adding to the intrigue, this isn't the only slowpoke out there. A handful of other pulsars like PSRJ 224, 1 plus 2156, which takes 11.8 seconds per spin, hint that our understanding of neutron star evolution has gaps. Each of these slow spinners forces astronomers to revisit assumptions about how magnetic fields decay, how internal structure affects rotation, and even how often these oddballs might be hiding in plain sight. What makes PSRJ 0250 plus 5854 truly remarkable isn't just its defiance of expectations, it's a reminder that the universe keeps rewriting the rules. For every cosmic phenomenon we think we've figured out, there's always an outlier waiting to prove the story is far more complicated than we imagined. Even the most precise cosmic clocks occasionally stutter. Neutron stars, renowned for their metronomic regularity, sometimes experience sudden speed-ups called glitches, millisecond jumps in rotation that defy their usual gradual slowdown. These bizarre hiccups aren't random malfunctions. They're violent outbursts of pent-up energy, like a frozen river cracking under pressure when the ice can no longer hold. The leading culprit, a neutron star's crust, a rigid shell of iron nuclei squeezed into a crystalline lattice, can fracture under the strain of the star's insane rotation and magnetic field. When it finally gives way, the crust lurches outward ever so slightly, like a figure skater pulling their arms in to spin faster. The effect is minuscule on a human scale, maybe a millimeter of movement across a 12-mile-wide star, but that tiny shift translates into a detectable speed boost for the entire object. But crust quakes alone don't explain every glitch. Some events point to something stranger happening beneath the surface. Deep inside the star, scientists suspect a sea of superfluid neutrons swirls with zero friction, like liquid helium chilled to absolute zero. Normally, this superfluid rotates in sync with the crust above it. But when vortices whirlpools in this quantum fluid suddenly unpin from the crust's underside, they transfer angular momentum outward like a sloshing cup of coffee kicked into motion. The result, a rotational kick strong enough to nudge the star's spin rate in a fraction of a second. The seismic parallels are striking. Just as earthquakes release built-up tectonic stress, starquakes relieve the tension between the neutron star's rigid crust and its turbulent interior. And like aftershocks, glitches often come in clusters, with smaller adjustments following the main event as the crust settles into a new equilibrium. Telescopes have even caught pulsars like Vela, a notorious glitcher speeding up multiple times over decades, each episode offering new clues about the star's hidden layers. What makes these events so valuable isn't just their drama, it's the window they provide into otherwise invisible physics. By studying glitches, astronomers can map the neutron star's internal structure, estimate the thickness of its crust, and even test theories about how superfluids behave under conditions no lab on Earth could replicate. Every sudden spin-up is a message in a bottle, hurled from the depths of a star where matter exists in states we're only beginning to imagine. Calvera should have been impossible to miss, a neutron star lurking just 250 light-years from Earth, closer than most stars visible to the naked eye. Yet this cosmic fugitive evaded detection until 2007, when astronomers combing through decades-old X-ray data stumbled upon its faint glow. Nicknamed after the villain from the Magnificent Seven, Calvera earned its name not just for its stealth, but for the mystery it represents. A neutron star with no past, no visible companions, and no explanation for how it wound up in our galactic backyard. Most neutron stars are found in the wreckage of their birthplaces, supernova remnants that linger for tens of thousands of years before dispersing. But Calvera floats alone in interstellar space, untethered to any visible debris cloud. Its isolation suggests it might be millions of years old, long outliving the glow of its parent explosion. Yet its X-ray emissions are strangely youthful, as if the star's surface hadn't fully cooled. This contradiction has scientists scrambling for answers. Did Calvera form in a rare, faint supernova that left no trace? Was it violently ejected from a binary system, flung across space like a bullet from a cosmic gun? Or does it belong to an entirely unknown population of neutron stars, dark, solitary wanderers hiding in plain sight? The implications are staggering. If Calvera isn't a fluke, there could be hundreds, even thousands, of similar objects drifting undetected between the stars. Their faint thermal X-rays would blend into the background noise of the galaxy, invisible to all but the most sensitive telescopes. Some might pass closer to Earth than Pluto, their gravity subtly tugging at the solar system's outer worlds without us ever noticing. What makes Calvera especially haunting is how little we still know. Its distance was only pinned down in 2021, thanks to precise measurements from the European Space Agency's Gaia mission. Even now, we can't say for certain whether it's spinning or how strong its magnetic field might be. It's a ghost in the data, challenging every assumption about where neutron stars should be and how many might be watching us from the shadows. The hunt for more Calveras is already reshaping how astronomers scan the skies. New X-ray surveys are searching for similar faint, isolated objects, while theorists model how neutron stars might migrate over millions of years. One thing's certain: if this star taught us anything, it's that the universe keeps its most intriguing secrets closer than we ever dared to guess. Neutron stars don't just warp space, they twist light itself into surreal mirages. Picture a star shining quietly billions of miles behind a neutron star. Normally, its light would sail straight toward us, invisible against the cosmic backdrop. But the neutron star's gravity bends space-time so severely that the distant star's light curves around it like water flowing around a boulder in a stream. The result, a ghostly optical illusion called gravitational lensing, where single stars appear doubled, stretched into arcs, or even smeared into perfect rings of light encircling the neutron star like a cosmic halo. Einstein predicted this effect over a century ago, but neutron stars take it to extremes. Their surface gravity is so intense, it can deflect light passing just a few miles above them by a full 45 degrees, enough to make background stars seem to shift positions entirely. In rare cases, like with the neutron star RxJ185 6.5375, this distortion creates what astronomers call an Einstein ring, a fiery circle of stretched starlight framing the neutron star's silhouette. These rings aren't just pretty, they're precision tools. By measuring their size and brightness, scientists can calculate the neutron star's mass with staggering accuracy, even from thousands of light years away. Simulations reveal even wilder possibilities. If a neutron star passed directly between Earth and a distant galaxy, its gravity could magnify and multiply the galaxy's image like a funhouse mirror, creating a kaleidoscope of duplicated quasars and warped spiral arms. The European Space Agency's Gaia mission has already spotted hints of these gravitational mirages, subtle shifts in starlight betraying unseen neutron stars drifting silently between us and the cosmic deep. What makes these shadows so valuable is their honesty. Unlike pulsar beams or X-ray glows, lensing depends purely on gravity, unaffected by magnetic fields or stellar spin. It's a direct window into the neutron star's most fundamental property, its weight, and sometimes it reveals even more. In 2021, Hubble caught a lensed star flickering unexpectedly, a clue that the warping neutron star might have a hidden companion, its gravity tugging subtly on the light show. These cosmic illusions remind us that even the darkest objects cast visible ripples. A neutron star might not emit light itself, but its gravity paints the sky with stolen brilliance, a reminder that in the vast theater of space, nothing, not even light, travels in straight lines. Somewhere in the depths of space, a story spread like wildfire, a planet made of solid diamond, glittering in the harsh light of a pulsar. It captured imaginations, inspiring headlines about the ultimate cosmic treasure. But here's the reality. The universe is strange enough without turning science into science fiction. The truth behind the so-called diamond planet PSR J1719-1438b is far weirder than any gemstone fantasy. Discovered in 2010, this system features a pulsar orbited by a small, dense world about 5 times Earth's mass. Early observations suggested it might be carbon-rich, sparking wild speculation about diamond cores. But the real story isn't about bling. Under the crushing gravity of that environment, carbon wouldn't form sparkling crystals. It would compress into exotic states we've never seen on Earth, layers of degenerate matter, perhaps even a sea of conductive carbon ice with properties closer to metal than mineral. The entire planet might resemble a colossal graphite pencil lead compressed into something unrecognizable. What makes this world truly bizarre isn't what it's made of, but how it exists at all. The pulsar it orbits is a millisecond pulsar spinning hundreds of times per second. Any planet that close to such a violent object should have been torn apart by radiation or vaporized long ago. Yet somehow this survivor clings on, its origins shrouded in mystery. Scientists suspect it might be the corpse of a white dwarf, a dead star stripped to its carbon core by the pulsar's relentless energy, leaving behind a grotesque, dense remnant. The real kicker, even if there were diamonds, they'd be inaccessible in every sense. Surface temperatures likely exceed thousands of degrees, with gravity so strong it would crush any probe into paste. And at 2,500 light-years away, it's not like we could mine it anyway. So next time you hear about diamond planets, remember space doesn't need embellishment to be wondrous. The universe's true oddities are hiding in plain sight, no cosmic jewelry required. Beneath the crushing weight of a neutron star's iron crust, a hidden inferno rages, not of molten rock but of nuclear fury. Scientists speculate that these cosmic monsters might harbor their own twisted version of volcanoes, where eruptions aren't powered by magma, but by the unimaginable pressures and nuclear reactions churning below the surface. Imagine a geyser not of lava, but of hyper-compressed neutrons and protons, forced upward through cracks in the crust by the star's own internal turmoil. These aren't your textbook eruptions, they're explosions of quantum-scale energy, blasting material into space at velocities approaching light speed. Evidence for these nuclear volcanoes comes from flickering X-ray hotspots spotted by telescopes like NASA Chandra. These bright, shifting patches on a neutron star's surface don't behave like steady thermal emissions. They flare and fade unpredictably, as if something beneath is occasionally punching through. Computer simulations suggest the culprit might be pockets of superfluid neutrons trapped beneath the crust like water in a shaken soda can. When the crust fractures under stress, these pressurized fluids could erupt in violent jets, carrying with them exotic particles and energy that ignite the X-ray fireworks we observe. The physics at play here is unlike anything on Earth. A neutron star's crust, while unimaginably dense, isn't uniform. It's riddled with defects, tiny weak points where the lattice of atomic nuclei, stretched to breaking by the star's rotation and magnetic field, might suddenly give way. When one of these microscopic faults ruptures, the release of pent-up energy could hurl material upward with the force of a nuclear bomb, creating transient volcanic plumes that glow fiercely in X-rays before collapsing back under the star's gravity. What's even wilder is how these eruptions might reshape the neutron star over time. Some theorists propose that repeated outbursts could dredge up heavier elements from deep within the star, slowly contaminating its surface with rare metals like gold or platinum. Others suggest these events might trigger chain reactions, destabilizing entire sections of crust and leading to massive starquakes. It's a delicate balance. Each eruption relieves pressure locally, but might load stress onto neighboring regions, setting the stage for even larger explosions down the line. The most tantalizing clue lies in a handful of neutron stars that exhibit bizarre, periodic X-ray bursts. These aren't the predictable pulses of a lighthouse like Pulsar, but irregular flares that hint at something bursting through the surface in fits and starts. Could these be the smoking guns of nuclear volcanism? Until we catch one in the act or simulate the conditions with next-generation quantum computers, the answer remains just out of reach. But one thing's certain. If neutron stars do have volcanoes, they're the most violent alien eruptions in the known universe, where the lava is a soup of subatomic particles and the energy released could power civilizations. And here's the kicker: these eruptions might be more than just a curiosity. If material blasted from a neutron star's surface collides with surrounding gas, it could create shock waves that accelerate particles to cosmic ray energies. Some of the high-energy radiation bombarding Earth right now might owe its existence to a nuclear volcano that erupted on a distant neutron star millions of years ago. Every flicker, every hotspot is a reminder that even in death, stars find ways to remake themselves and the cosmos around them. Sizu J061705.3 plus 222127 isn't just another neutron star. It's a cosmic fugitive hurtling through the void at a staggering 4 million miles per hour. Unlike most of its kind, which linger near their birthplaces, this rogue has been violently ejected from its home galaxy, destined to drift alone through the abyss between galaxies for eternity. How does a stellar corpse wind up banished into intergalactic exile? The answer lies in one of the universe's most brutal breakups, a supernova gone wrong. When a massive star dies in a supernova, the explosion isn't always perfectly symmetrical. If the blast is lopsided, kicking harder in one direction than the other, the newborn neutron star can be launched into space like a bullet from a rifle. But sometimes the star isn't alone. In binary systems where two stars orbit each other, the supernova's violence can detonate with such force that the surviving neutron star gets flung away at speeds that defy gravity's grip. Sizu J061705.3 plus 222127 likely endured this exact scenario, catapulted into the darkness by a cosmic slingshot of its own making. What's astonishing isn't just its speed, it's the loneliness. Most neutron stars are anchored to the Milky Way by gravity, but this one moves so fast it's escaped entirely. Current trajectory estimates suggest it's already crossed into intergalactic space, where the nearest star is thousands of light years away. Without a galaxy's gas and dust to slow it down, this rogue will keep racing indefinitely, its faint X-ray glow fading into the background hum of the cosmos. Yet even in isolation, it's not entirely dark. The star's magnetic field still accelerates particles, creating a bow shock, a visible ripple in the sparse intergalactic medium, like the wake of a ship plowing through still water. Telescopes have spotted this faint shimmer, a ghostly signature of its passage, and there's a haunting beauty to its journey, Long after every star in its birthplace has died, this lone wanderer will still be traveling, a relic of a galaxy that no longer exists. The discovery of hypervelocity neutron stars forces us to rethink how many might be hiding in the voids between galaxies, invisible to all but the most sensitive instruments. If CZU J061705.3+222127 is any indication, the cosmos might be teeming with these exiled remnants, each one a silent witness to the violent, unpredictable nature of stellar death. And who knows, some might even be hurtling toward us, destined to pass through our galactic neighborhood millions of years from now, leaving only the faintest trace of their impossible speed. Some neutron stars don't just shine, they whisper, sending faint echoes of their brilliance bouncing through the cosmos. When a burst of X-rays from a spinning pulsar slams into nearby clouds of interstellar dust, something extraordinary happens. Like a flashlight beam hitting a foggy mirror, the radiation scatters, creating ghostly afterimages that linger long after the initial flash. These light echoes aren't just cosmic curiosities, they're time machines, allowing astronomers to reconstruct events that happened centuries before telescopes ever caught them in the act. Take the case of Circinus X1, a neutron star discovered by NASA Chandra X-ray Observatory. In 2010, Chandra caught eerie rings of X-rays expanding outward from the star like ripples in a pond. Those rings weren't emitted by the star itself, they were reflections, the aftermath of a powerful flare that had erupted 50 years earlier. The X-rays from that long-ago explosion had traveled outward until they hit dense curtains of cosmic dust, some lying 600 light-years from the star. Each dust cloud acted like a celestial mirror, bouncing a portion of the radiation back toward Earth, but with a delay. The farther the cloud, the longer the light took to return, creating multiple overlapping echoes that painted a timeline of the original event. What makes these echoes so invaluable is their forensic detail. By mapping the rings' precise shapes and intensities, scientists can reverse engineer the neutron star's outburst down to the minute. They've even used them to measure distances across interstellar space with pinpoint accuracy, triangulating the positions of dust clouds that would otherwise be invisible. In some cases, like with the neutron star B0617-20, the echoes revealed previously unknown structures, vast, filamentary tendrils of dust stretching hundreds of light-years, sculpted by ancient supernova or stellar winds. But the real magic lies in how fleeting these echoes are. Unlike pulsar beams that flash predictably for millennia, light echoes fade within decades as the radiation disperses. Catching them requires both luck and precision. Chandra's sharp X-ray vision can distinguish echoes separated by mere arcseconds on the sky, a feat like spotting individual grains of sand on a beach from orbit. And because each echo carries a spectral fingerprint of the dust it bounced off, astronomers can even deduce the cloud's composition, whether it's rich in silicates, graphite, or ice, without ever touching it. The most haunting implication: some of the echoes we see today might be from neutron stars that have since gone quiet or vanished entirely. Their light, traveling for centuries, still reaches us as faint, expanding halos, a final testament to their fury. And who knows how many other echoes are out there, undetected, carrying stories of cosmic violence we've yet to uncover. Every ripple in the X-ray fog is a message from the past, waiting for someone to listen. Just when scientists thought they had neutron stars figured out, along came one that didn't just break the rules, it rewrote them entirely. In 2012, astronomers monitoring the neutron star 1E2259+586 witnessed something that defied all expectations. Instead of suddenly spinning faster like clockwork glitches predict, the star slowed down without warning. This baffling phenomenon, dubbed an anti-glitch, sent shockwaves through the astrophysics community, forcing a complete re-examination of what might lurk beneath a neutron star's impenetrable crust. The mechanics of an anti-glitch flip everything we know about neutron star behavior on its head. Ordinary glitches, those sudden speed-ups, happen when the star's rigid crust fractures or its interior superfluid vortices unpin, transferring angular momentum outward like a spinning ice skater pulling in their arms. But an anti-glitch suggests the opposite. Something inside the star is stealing rotational energy, applying invisible brakes with no obvious explanation. One leading theory points to the star's monstrous magnetic field. If parts of the crust became temporarily locked to the magnetic field lines, which themselves might be slowly rearranging, the resulting drag could sap the star's spin in a sudden, measurable drop. Others speculate that anti-glitches might involve a hidden, chaotic dance beneath the surface. Imagine a neutron star's core as a churning ocean of superfluid neutrons swirling with zero friction. Normally, this fluid rotates in sync with the crust above it. But if a chunk of this superfluid were to suddenly pin itself to the crust like a parachute snapping open in a hurricane, the resulting friction could rapidly drain energy from the star's spin. Computer simulations have shown that under just the right conditions, these superfluid tangles might generate the exact slowdowns observed in 1E2259 plus 586. The real puzzle, though, is how rare these events are. Of the thousands of monitored neutron stars, only a handful, like the Vela pulsar, have shown possible anti-glitch behavior, and even those cases remain hotly debated. This scarcity makes each detection a goldmine for physicists. Unlike ordinary glitches, which are practically routine, anti-glitches demand exotic explanations, perhaps even hinting at phases of matter we've yet to discover. Could there be pockets of strange quark matter inside these stars, momentarily freezing and altering the spin? Or are we seeing the fingerprints of magnetars, whose unruly magnetic fields twist the rules of physics entirely? The irony is delicious. Neutron stars, often praised as the universe's most precise clocks, occasionally throw tantrums that leave scientists questioning the very laws they're supposed to embody. Every anti-glitch is a humbling reminder that beneath their seemingly predictable surfaces, these stellar corpses hide layers of chaos we've only begun to unravel. And until the next one strikes, all we can do is watch, wait, and wonder what other surprises these cosmic enigmas have in store. The moment you stray too close to a neutron star, gravity stops playing fair. Forget the gentle tug of Earth's pull. This is a force so monstrous, it would stretch you into a strand of cosmic spaghetti long before you ever hit the surface. Picture a rubber figure drifting toward the star. At first, nothing seems amiss, but as you cross the invisible boundary where the star's gravitational grip overwhelms your body's structural integrity, every atom in you would experience a different intensity of pull. Your feet, just slightly closer to the star than your head, would feel a fiercer yank downward. The difference might seem microscopic, but on a neutron star, that infinitesimal gap spells doom. The math behind this spaghettification is chilling. A typical neutron star's surface gravity is around 100 billion times stronger than Earth. At a distance of 6,000 miles well above the surface, the tidal forces would already exert a differential pull of over 15,000 Gs across a 6-foot-tall human. That's enough to stretch you like taffy, elongating your body into a thin, screaming filament of atoms, and you wouldn't even need to be near the star's surface for this nightmare to unfold. Most neutron stars are so compact, their lethal tidal zone begins thousands of miles out, far beyond where any spacecraft could hope to break. Animations love to depict this gruesome process with a whimsical rubber figure, limbs flailing as they're drawn into a comical noodle shape. But reality is far more violent. Your bones would snap first, then your muscles and tendons, all while your bloodstream splits into parallel rivers of plasma racing toward your feet and head. By the time your stretched-out remains reach the surface, If you even existed as a coherent structure anymore, you'd be less a person and more a stream of subatomic particles smeared across the crust. What makes this even wilder is the timescale. Unlike a black hole where tidal forces might rip you apart in seconds, a neutron star's spaghettification would be near instantaneous. At 15% the speed of light, your elongated atoms would slam into the surface so fast the impact would trigger a burst of X-rays, a morbid farewell firework detectable by telescopes light years away. The irony, these same tidal forces make neutron stars cosmic gold factories. When two collide, their gravitational fury rips apart their crusts, flinging neutron-rich material into space where it fuses into heavy elements like gold and platinum. So while getting too close to one would be a gruesome end for you, it's those very forces that sprinkle the universe with the ingredients for jewelry, electronics, and even life itself. A small consolation, maybe, but a reminder that in space, even destruction can be breathtakingly creative. In the cosmic graveyard of dead stars, some neutron stars refuse to stay buried. These celestial zombies claw their way back to life by feasting on their stellar companions, transforming from dim remnants into blazing X-ray pulsars that light up the sky. The process begins when a neutron star silent for millennia wanders too close to a living star. Gravity does the rest, pulling gas from the companion's outer layers onto the neutron star's surface in a slow, relentless drip. As this stolen material crashes onto the neutron star, it doesn't just pile up quietly. The infalling gas accelerates to nearly half the speed of light, heating up to millions of degrees and igniting in violent thermonuclear explosions. These outbursts flood space with high-energy X-rays, announcing the neutron star's resurrection to the universe. Suddenly, what was once a cold, dark corpse becomes a pulsar again, its magnetic funnel focusing the X-rays into beams that sweep across space like a lighthouse reborn. The revival isn't gentle. Systems like Centaurus X3 demonstrate the brutality of this process, where the neutron star's gravity strips entire atmospheres from its companion, leaving behind a scarred, half-eaten star. In extreme cases, the influx of material can even spin the neutron star up to dizzying speeds, turning it into a millisecond pulsar that whips around hundreds of times per second. It's a cosmic paradox. The very act of cannibalizing another star breathes new life into the dead one. What's fascinating is how unpredictable these rebirths can be. Some neutron stars, like Aquila X1, flicker between active and quiescent states for centuries, flaring up whenever they gorge on fresh material. Others undergo dramatic transitions, like the famous PSRJ-102 3+0038, which spent decades as a quiet radio pulsar before suddenly erupting in X-rays when its appetite returned. These zombie stars are more than just celestial oddities, they're time capsules. By studying their outbursts, astronomers can trace the history of binary systems, measure how neutron stars evolve over cosmic timescales, and even probe the physics of accretion disks under extreme gravity. Every flare, every pulse is a reminder that in the universe, death isn't always permanent. Sometimes it's just an opportunity for a second act. Deep inside a neutron star, matter doesn't just get crushed, it transforms into something beyond atoms, beyond nuclei, even beyond neutrons themselves. At these unimaginable pressures, protons and electrons cease to exist as distinct particles, and the neutrons that replace them might not even be the end of the story. Scientists suspect the core of a neutron star could be a swirling ocean of quarks, the fundamental building blocks of all matter, unchained from their usual confines and set loose in a seething, ultra-dense plasma. This isn't just dense matter, this is quark-gluon plasma, a state of existence so extreme it hasn't been seen naturally since the first microseconds after the Big Bang. The conditions required to create this quark soup defy earthly imagination. we're talking about pressures 100 trillion times greater than Earth's atmosphere, with temperatures soaring past 10 trillion degrees. At these extremes, the boundaries between individual neutrons dissolve, their constituent quarks normally locked together by the strong nuclear force, spilling free into a chaotic, seething broth. Theoretical physicists call this exotic state quark matter, and some speculate it might take an even weirder form, strange matter, a hypothetical substance where up and down quarks mingle with their heavier, unstable cousin, the strange quark. If this exists, it could be the most stable form of matter in the universe, capable of converting anything it touches into more strange matter in a runaway reaction that would rewrite the laws of physics as we know them. Why don't we know for sure if neutron star cores are made of this bizarre substance? Because replicating these conditions on Earth is like trying to recreate a hurricane inside a soda can. Particle colliders like the Large Hadron Collider can briefly produce quark-gluon plasma by smashing heavy nuclei together at near light speeds. But these flashes last mere fractions of a second and occupy a space smaller than an atom. Neutron star cores, by contrast, sustain these conditions for millions of years across a region the size of a city. The gap between our lab experiments and cosmic reality is so vast, even the most advanced simulations strain under the computational weight. Even the equations themselves start to break down. Quantum chromodynamics, the theory governing quark behavior, becomes fiendishly complex at these densities. Supercomputers running lattice QCD calculations can only approximate small slices of the problem before the math spirals into unsolvable chaos. It's like trying to predict every ripple in a tsunami while standing in the surf. Without direct observations of a neutron star's interior, something even gravitational waves can't yet provide, we're left piecing together clues from indirect hints. The way a neutron star cools, how it wobbles during a glitch, or the maximum mass it can reach before collapsing into a black hole. Some theories push the strangeness even further. A handful of physicists propose that under enough pressure, quark matter might crystallize into a quark star, with a solid core of layered quark arrangements unlike anything in nature. Others suggest the core could harbor free-floating gluons, the particles that normally mediate the strong force, forming a glowing, frictionless superfluid that permeates the entire star. And if strange matter exists, it might ooze up through cracks in the crust during starquakes, creating fleeting bursts of exotic radiation we've yet to identify. The question isn't just academic. If quark matter is stable enough to exist in neutron star cores, it could mean the universe is littered with quark nuggets, leftover fragments from the early cosmos that could be lurking in dark matter detectors or even passing through Earth unnoticed. Some have even speculated that certain mysterious ultra-high-energy cosmic rays might be shrapnel from quark matter collisions in distant galaxies. Every glitch, every gravitational wave detection, and every precision measurement of a pulsar's mass brings us slightly closer to answering the riddle of what lies beneath that iron crust. Until then, the core of a neutron star remains one of the last great frontiers of extreme physics, a realm where matter itself is pushed to the breaking point, and the only certainty is that reality is far stranger than we've dared to dream. When a star explodes as a supernova, it's supposed to leave behind a calling card, either a neutron star blinking in the wreckage or a black hole silently lurking in the dark. But sometimes the universe plays hide and seek. Take SN 1987A, the closest observed supernova in 400 years. This stellar detonation should have forged a neutron star so bright we'd spot it from Earth even 37 years later. Yet despite decades of searching with Hubble, Chandra, and even the James Webb Space Telescope, the aftermath remains eerily empty, no pulsing beacon. No glowing ember, just a question mark hanging in the dust. This cosmic vanishing act isn't unique. Of the thousands of supernova remnants catalogued, nearly a third lack any visible compact object at their core. Some might blame obscuring dust supernova blast out enough debris to shroud a neutron star like fog around a lighthouse. In SN 1987A's case, models suggest the missing object could be buried under 20 trillion tons of stellar ejecta, its light swallowed before reaching us. But there's a darker possibility. What if the star didn't leave a neutron star at all? If the collapsing core was too massive, it might have skipped the neutron star phase entirely, imploding straight into a black hole without fanfare. The implications unsettle astronomers. Current theories predict a strict mass limit for neutron stars around 2.2 solar masses. Cross that threshold and gravity wins, crushing the core past the point of no return. But stars are messy. Rotation, magnetic fields, and even the speed of collapse could tweak that limit, allowing some cores to teeter on the edge before vanishing. SN 1987A's progenitor star weighed in at 18 solar masses, right in the theoretical danger zone where outcomes get unpredictable. Some clues hint at a hidden survivor. Recent infrared observations of SN 1987 show a peculiar blob of emission near the explosion center, too hot to be ordinary debris. Could this be the thermal glow of a young neutron star? It's BODY Chinese letter, but still simmering at 500,000 degrees. Or perhaps a pulsar's energetic wind, trapped in a cocoon of dust and glowing faintly in the shadows. Until we peer deeper, or until the debris clears centuries from now, the mystery endures. The missing neutron star problem forces us to confront gaps in our stellar death models. Maybe some neutron stars form quieter than expected, their magnetic fields too weak to power visible pulsars. Others might receive a natal kick so violent they rocket away from their birth sites before we can spot them. And then there are the black hole scenarios where collapse happens so fast it leaves no trace beyond gravity's fingerprints on surrounding gas. Every empty supernova remnant is a riddle wrapped in an enigma, challenging us to rethink how stars die and what they leave behind. The universe, it seems, has a flair for drama, keeping its finales as ambiguous as they are spectacular. Neutron stars don't just spin, they thrum, vibrating with rhythmic X-ray pulses that act like cosmic EKGs for these stellar corpses. These aren't the steady ticks of a radio pulsar. They're erratic, stuttering flickers known as quasi-periodic oscillations, or QPO. Picture a heart monitor hooked up to a dying star, its beats fluttering between rapid spikes and slow, shuddering lulls. For astrophysicists, these X-ray tremors are more than just noise. They're a direct line into the neutron star's chaotic inner workings, revealing details about its magnetic fields, surface quakes, and even the swirling maelstrom of gas being devoured from a companion star. The most revealing QPOs come from X-ray binary systems, where a neutron star feasts on material ripped from a neighboring star. As this stolen gas spirals inward, it forms a seething accretion disk that glows white-hot before slamming onto the neutron star's surface. The process isn't smooth. Clumps of plasma crash down at uneven intervals, creating X-ray flickers that rise and fall in semi-regular patterns, like a faucet dripping at almost, but not quite, the same speed. These QPOs cluster into two bizarre categories. Low-frequency rumbles, think a bass drum thumping every few seconds, and high-frequency tremors, more like a snare drum roll at hundreds of beats per second. The wild part, these frequencies aren't random. They're tied to fundamental physics happening just miles above the neutron star's surface. Low-frequency QPOs likely originate in the turbulent outer edges of the accretion disk, where gas churns like storm clouds before plunging toward the star. Astronomers compare these oscillations to the vibrations of a plucked guitar string. The disk's rotation creates standing waves that reverberate at specific harmonics. High-frequency QPOs, though, are far more exotic. These rapid-fire pulses might stem from blobs of plasma ricocheting near the neutron star's magnetic poles, or from vibrations in the star's own crust triggered by the constant bombardment of infalling material. Some theories even suggest high-frequency QPOs could be tracing the innermost stable orbit around the star, the point where spacetime itself is so warped, gas can no longer circle safely and instead spirals straight down. One of the most famous QPO producers is the neutron star Jaris 19-1, 1+105 in the constellation Aquila. Every few years, this system erupts in X-ray outbursts, its QPOs shifting frequencies like a cosmic slide whistle as the accretion rate changes. During one particularly violent episode, astronomers caught QPOs and their harmonics multiple frequencies locked in perfect mathematical ratios like notes in a chord. This wasn't just cosmic noise, it was a symphony of precision, revealing the neutron star's immense gravity was tuning the accretion disk's vibrations like the pipes of an organ. But QPOs aren't just academic curiosities. Their frequencies encode the neutron star's mass and radius with startling accuracy. By comparing the timing of these oscillations to general relativity predictions, scientists can effectively weigh the star without ever touching it. Some teams have even used QPOs to test Einstein's theory under extreme gravity, searching for subtle deviations that might hint at new physics. And when QPOs suddenly vanish, as they did during a bizarre quiet state, observed in the system MXB 1658-29, it suggests something radical is happening, like the magnetic field momentarily choking off the flow of gas entirely. The real magic lies in how something as fleeting as an X-ray flicker can unveil the invisible. A single QPO might last milliseconds, but its fingerprint lingers in telescope data like a ghostly echo. By decoding these tremors, we're not just listening to a dead star's heartbeat, we're mapping the forces that govern the most extreme environments in the universe. And with every new pulse, every shift in rhythm, these stellar corpses remind us that even in silence, they're screaming secrets across the cosmos. Most cosmic clocks tick with unwavering precision, but PSRB 0943+10 is the pulsar that can't make up its mind. Nicknamed the chameleon for its bizarre ability to flip between two distinct personalities, this neutron star alternates between brilliant X-ray fury and near-silent radio whispers without warning. One moment, it's blazing like a lighthouse at full power, its radio pulses strong enough to pierce interstellar static. The next, it's faded to a murmur as if someone flipped a cosmic dimmer switch. What makes this behavior so baffling isn't just the shift, it's the speed. Unlike glitches or gradual slowdowns, the chameleon transitions in seconds with no buildup or aftereffects. In its bright, radio-loud mode, its surface likely bristles with plasma-filled magnetic loops, funneling radiation into coherent beams. But when it flips to its quiet X-ray dominant state, those structures might collapse or reconfigure, like a neon sign flickering off as its gas supply cuts out. The strangest part, the two modes aren't just different volumes, they're entirely different languages. The radio pulses vanish completely in X-ray mode, replaced by a thermal glow suggesting the star's surface is suddenly hotter, as if its internal engine switched fuel. Astronomers suspect this Jekyll and Hyde act stems from the pulsar's magnetosphere, the zone where its magnetic field rules supreme. In one configuration, charged particles flood the magnetic poles, creating the conditions for crisp radio beams. But a slight rearrangement, perhaps triggered by cascading fractures in the crust or a sudden influx of particles, could send the system into chaos, disrupting the radio emission and letting trapped heat bubble to the surface instead. Some theorists compare it to a cosmic version of a clogged drain. Normally, the pulsar's rotation and magnetic field work in tandem to keep particle flow steady. But if debris, maybe fragments from past starquakes or interstellar material, temporarily jams the magnetic pipes, the whole system backs up, rerouting energy inward until the blockage clears. Others propose a more elegant explanation. The star's magnetic axis might be wobbling like a spinning top, periodically tilting its beams away from Earth while exposing hotter, X-ray bright regions normally hidden beneath the surface. The chameleon isn't alone in this behavior. A handful of other pulsars like PSRB 1822-09 show similar mode switching, but none as dramatically or unpredictably. What sets PSRB 0943 plus 10 apart is the sheer contrast between its states. It's not just turning a dial up or down, it's rewriting its entire playbook mid-performance. For astronomers, this pulsar is a Rosetta Stone for neutron star magnetospheres. By catching it mid-flip, something telescopes like Chandra and Arecibo have managed only a handful of times, they can glimpse the invisible scaffolding that governs how these stars channel their energy. Every erratic pulse, every silent stretch is a breadcrumb, leading us closer to understanding why some neutron stars shine steady while others flicker like candles in the cosmic wind. One thing's certain, the universe loves a good plot twist. Just when we think we've mapped the rules, along comes a star that plays by its own. A newborn neutron star doesn't just emerge from a supernova, it gets kicked into the cosmos like a cosmic bullet. These stellar remnants often rocket away at speeds exceeding 500 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 15 minutes. What could possibly launch something with the mass of a sun so violently? The answer lies in the chaos of their birth, specifically, the imperfections hidden in what should be a perfectly symmetrical explosion. Supernova aren't tidy detonations. When a massive star collapses, the implosion rebounds into an explosion, blasting the outer layers into space. But if this explosion is even slightly lopsided, perhaps due to turbulent convection in the dying star's core or a misaligned rotation axis, the recoil acts like a rocket engine gone haywire. Imagine a fire hose thrashing uncontrollably as water erupts from one side more forcefully than the other. In a supernova, that unequal thrust from neutrinos and ejected matter doesn't just propel debris, it hurls the neutron star itself in the opposite direction, a phenomenon called the birth kick. The physics of these kicks is mind-bending. During the collapse, trillions of neutrinos flood outward at near light speed, carrying away immense energy. If they exit asymmetrically, preferentially streaming from one hemisphere, their momentum can shove the neutron star like a sailboat caught in a gust. Simulations show that just a 7% imbalance in neutrino emission is enough to accelerate the star to 700 kilometers per second. Add to that the uneven ejection of stellar material, and you've got a cosmic slingshot capable of launching neutron stars clear out of their host galaxies. Real-world examples are even wilder. Take the neutron star B0911 1+06, clocked at over 1,500 kilometers per second, so fast it's destined to escape the Milky Way entirely. Or the Black Widow pulsar, streaking through space with enough velocity to leave its companion star disintegrating in its wake. These hypervelocity escapees challenge our understanding of stellar mechanics, proving that supernova are far from the orderly, spherical blasts textbooks often depict. But here's the twist: not all neutron stars receive extreme kicks. Some, like the one at the heart of the Crab Nebula, barely budged from their birthplace, suggesting their supernova were remarkably balanced. This split personality, wild runners versus quiet stay-at-homes, hints at deeper mysteries. Could magnetic fields play a role in stabilizing some explosions? Or do binary systems, where a companion star's gravity steers the collapse, produce gentler kicks? The implications ripple across astronomy. These runaway neutron stars become galactic pioneers, seeding interstellar space with heavy elements and potentially even delivering the building blocks of life to new star systems. Others, like the famous Calvera, wind up shockingly close to Earth after millions of years, adrift reminders that the cosmos is far more dynamic and far less predictable than we ever imagined. Every high-velocity neutron star is a fossil record of its supernova's final moments, a clue etched in motion about how stars die, and how the universe flings its most exotic creations into the void. Not all neutron stars announce themselves with flashing radio pulses or searing X-rays. Some lurk in the shadows, detectable only by their faintest whispers of gamma radiation. Take HES J1731-347, a celestial oddity that defies categorization. Discovered by the High-Energy Stereoscopic System HES array in Namibia, this object sits silently in the constellation Scorpius, radiating high-energy gamma rays while stubbornly refusing to emit the radio or X-ray signals typical of its kind. It's as if the star has chosen to communicate in a language we barely understand, leaving astronomers scrambling to decode its secrets. What makes HES J1731-347 so perplexing isn't just what it lacks, it's what it doesn't lack. Most gamma-ray sources in the galaxy are tied to obvious cosmic powerhouses: pulsars with their spinning beams, supernova remnants with their shockwaves, or black holes devouring stars. But this object stands alone, a gamma-ray hotspot with no visible engine. One leading theory suggests it might be a radio-quiet neutron star, its magnetic field too weak to generate the usual lighthouse-like radio pulses, or its beams might simply miss Earth entirely. Alternatively, it could be an exotic hybrid, a neutron star cloaked in a thick shroud of debris from its birth supernova. Its X-rays absorbed before they can escape, while gamma rays punch through the veil. The plot thickens when you consider its surroundings. Unlike most neutron stars, which light up their birth nebulae for millennia, HES J1731-347 floats in a region suspiciously devoid of supernova wreckage. This raises the tantalizing possibility that it wasn't born in a traditional stellar explosion at all. Could it be the remnant of a failed supernova, where a massive star collapsed quietly into a neutron star without the usual fireworks? Or might it be the descendant of a Thorn-Zitkow object, the hypothetical zombie star we discussed earlier, having shed its red giant envelope and now drifting unseen? Even its gamma rays tell a strange story. The emissions aren't steady, they flicker in ways that don't match any known pulsar profile. Some researchers speculate these fluctuations could hint at an invisible companion, a cold, dim star or a debris disk interacting erratically with the neutron star's magnetic field. Others wonder if we're seeing the fallout of a recent starquake, with the crust's fractures unleashing bursts of gamma-ray energy like tectonic slips triggering earthquakes. The hunt for answers has turned into a cosmic detective story. Telescopes from radio dishes to X-ray satellites have trained their gaze on this region, each returning empty-handed. The James Webb Space Telescope might finally crack the case, peering through obscuring dust to spot any infrared glow from a hidden disk or companion. Until then, HES J1731-347 remains a ghost in the gamma-ray fog, a reminder that for every neutron star we think we understand, there's another out there rewriting the rules. And it's not alone. Objects like it, gamma-ray sources with no obvious counterparts, are cropping up in surveys with unsettling frequency. Each one forces us to question whether we've been too narrow in defining what a neutron star can be. Perhaps the cosmos has been hiding an entire population of dark neutron stars all along, their signatures too subtle for our current tools to grasp. If so, the universe just got a lot more interesting and a lot more mysterious. Some neutron stars don't just spin quietly in the void, they feast. Locked in a cosmic dance with a neighboring star, these celestial predators slowly siphon off their companion's lifeblood, growing denser and more massive with every stolen breath of gas. It's a slow-motion act of cannibalism that can last for millions of years, a gravitational waltz where one partner grows stronger while the other withers away. And if the neutron star gets too greedy, this deadly tango can end in catastrophe. The moment it gorges itself past a critical threshold, collapsing into a black hole without warning. The process begins with an innocent-looking binary system, Two stars born together orbit each other peacefully until one explodes as a supernova, leaving behind a neutron star. What happens next is a masterclass in gravitational theft. The neutron star's immense pull starts peeling away layers of its companion's outer atmosphere, funneling gas into a swirling disk of superheated plasma called an accretion disk. Time-lapse simulations of these systems reveal the horror in hypnotic detail. Tendrils of stellar material stretching toward the neutron star like taffy, spiraling inward at nearly the speed of light before slamming onto its surface in a flash of X-rays. Each bite stolen from the donor star adds mass to the neutron star, sometimes as little as a billionth of Earth's weight per second, but over millennia it adds up. But there's a terrifying tipping point. Neutron stars can only withstand so much before gravity wins. Current theories suggest that around 2.2 times the mass of our Sun, the internal pressure from neutrons resisting collapse fails. At that critical moment, the star's core buckles, and in less than a second, the entire object implodes into a black hole. Simulations show this transformation isn't always violent. Sometimes, the neutron star simply vanishes from observations, its light snuffed out as an event horizon swallows it whole. Other models depict a final, desperate burst of gamma rays as the star's magnetic field snaps like a rubber band stretched too far, signaling its demise. The aftermath is just as dramatic. When the neutron star vanishes, its companion, now robbed of the gravitational anchor that shaped their orbit, might be flung into space like a slingshot. Alternatively, if the black hole remains, it could continue feeding, this time with even more devastating efficiency. Telescopes have caught these systems mid-feeding frenzy, like the infamous JURS 1915+105, where X-ray flickers betray the black hole's relentless appetite. What makes these binary banquets so valuable to scientists isn't just their brutality, it's the clues they hold about the universe's most extreme physics. The rate of mass transfer reveals how matter behaves under crushing gravity, while the X-ray spectra of accretion disks act as cosmic barometers, measuring conditions no lab could replicate. Some of these cannibalistic neutron stars even flirt with the mass limit for decades, teetering on the edge of collapse, offering a front-row seat to how matter surrenders to oblivion. Perhaps the most haunting thought, every gold atom in your jewelry, every uranium nucleus in Earth's crust, might owe its existence to a neutron star that crossed this line long ago. When these objects collapse, their final moments can unleash torrents of neutron-rich material into space, the very ingredients for heavy elements. So while the act of stellar cannibalism ends in destruction, its legacy is written in the chemistry of planets, life, and even us. The universe, it seems, recycles tragedy into creation. Even the fastest rockets humans have built crawl through space compared to the supersonic gales racing from some neutron stars. These aren't ordinary stellar winds, these are pulsar winds, hurricanes of charged particles screaming outward at 99.9% the speed of light. Early astrophysicists dismissed the idea as fantasy, arguing no cosmic object could sustain such velocities without tearing itself apart. Yet telescopes have since caught these hypervelocity outflows red-handed, their existence forcing a total rewrite of how energy escapes from stellar corpses. The mechanics behind these winds start with the neutron star's dizzying spin and apocalyptic magnetic fields. As the star rotates, its magnetic field whips through space like an invisible lasso, accelerating electrons and protons to relativistic speeds. But here's where classical physics breaks down. These particles don't just trickle away. They erupt in a structured frenzy, organized into twin jets blasting from the magnetic poles and a turbulent equatorial outflow resembling a cosmic hurricane. The Vela Pulsars Wind Nebula showcases this beautifully. X-ray images reveal delicate tendrils of energized particles stretching light years into space, their patterns frozen in mid-eruption like a photograph of an explosion. What makes these winds impossible by early standards is their sheer efficiency. Traditional models assumed particles would lose energy through collisions or magnetic drag long before reaching such speeds. But pulsar winds cheat, exploiting a loophole in plasma physics. The star's magnetic field doesn't just push particles, it flings them outward in a coordinated slingshot motion, with each charged particle surfing the collapsing waves of magnetic energy like a surfer catching an endless tidal wave. Simulations show these waves can transfer energy near perfectly with minimal loss to heat or radiation, effectively creating a particle accelerator the size of a solar system. The Crab Nebula offers the most dramatic case study. At its heart, the Crab Pulsar's wind generates enough power to light up the entire nebula, energizing filaments of gas that glow across the electromagnetic spectrum. But the real marvel lies in the wind's composition. It's not just electrons and protons. Antimatter positrons stream out in equal abundance, their creation tied to quantum processes near the star's surface where magnetic reconnection events act like natural particle colliders. This matter-antimatter hurricane slams into slower-moving nebula gas, creating shock fronts that glow in gamma rays, visible light, and radio waves simultaneously. Yet for all their fury, these winds are precision instruments. The fastest millisecond pulsars, those spun up by accreting matter from a companion, produce winds so finely tuned, their particles exhibit less than 1% variation in velocity across light years of travel. It's as if the star has an invisible throttle regulating the outflow with engineering-grade precision. The implications ripple far beyond neutron stars themselves. These winds are cosmic sculptors, carving cavities in interstellar gas and seeding galaxies with high-energy particles that might kickstart star formation in distant clouds. Some researchers even speculate that positrons from ancient pulsar winds could explain mysterious excess antimatter detected around Earth. Every time a neutron star's breath streaks across the cosmos, it's not just defying expectations, it's rewriting the rules of how energy, matter, and momentum can traverse the universe. The lesson when it comes to neutron stars, impossible, is just a challenge waiting to be overturned. In July of the year 1054, Chinese astronomers recorded a guest star so bright it outshone Venus and remained visible in daylight for 23 days. This celestial visitor wasn't a comet or a wandering planet. It was the violent death of a massive star, an explosion we now know as the supernova that birthed the Crab Nebula. Nearly a millennium later, modern telescopes revealed the hidden legacy of that cataclysm. A neutron star spinning 30 times per second at the nebula's heart, its rhythmic pulses perfectly synchronized with descriptions from ancient scrolls. This extraordinary continuity, linking an event witnessed by Song Dynasty skywatchers to an object studied by orbiting X-ray observatories today, makes the Crab Pulsar humanity's longest observed cosmic laboratory. The connection goes deeper than historical coincidence. By cross-referencing medieval records with the pulsar's current behavior, astronomers have calculated its spin-down rate with unprecedented precision. Ancient texts describe the supernova's fading glow over 2 years, matching modern models of how expanding debris gradually obscures a neutron star's light. Even more strikingly, the pulsar's rotational energy loss aligns perfectly with the nebula's present expansion speed, as if the universe left us a 1,000-year time lapse to verify its physics. But the Crab Nebula isn't unique. Korean records from the year 1006 describe another guest star in the constellation Lupus, now identified with the neutron star PSRJ 1119-6121. Unlike the Crab's vibrant remnant, this pulsar drifts through near-empty space, its birth nebula long dispersed, yet its rotation period and magnetic field betray an age that matches the ancient sighting. Similarly, the supernova of 1181, documented by Japanese and Chinese astronomers, likely produced the neutron star 3C58, whose X-ray glow still bears the scars of that explosion 8 centuries later. What makes these cosmic echoes so valuable is how they ground theoretical models in observable reality. When simulations suggest a neutron star should spin a certain way after 900 years, the Crab pulsar's actual behavior either confirms or refutes those predictions with hard data. The historical sightings act as calibration points, letting scientists test stellar evolution theories across timescales no computer could simulate. For instance, the absence of neutron stars linked to certain ancient supernovae hints that some massive stars might collapse directly into black holes without the usual fireworks, an idea bolstered by the missing compact object in Kepler's supernova remnant from 1604. Perhaps the most haunting connection lies in cultural memory. The Crab Nebula's ancestor star likely detonated 6,500 years before its light reached Earth, meaning Neolithic humans were already painting on cave walls when the event actually occurred. That the explosion's afterglow would later be recorded by astronomers writing on silk and parchment, then studied by satellites millennia later, creates an unbroken thread of human curiosity stretching from prehistoric skygazers to modern astrophysicists. Every pulse from the Crab pulsar isn't just a beacon of physics, it's a message across time, reminding us that the universe keeps its schedules on scales far grander than our own. Some neutron stars whisper where others scream, revealing themselves not through flashing radio pulses, but through faint X-ray murmurs that only the most sensitive telescopes can catch. Take the dense remnant hiding inside Cassiopeia A, the expanding wreckage of a star that exploded around 300 years ago. For decades, astronomers scanned this supernova remnant for the telltale radio pulses of a pulsar and found nothing. It wasn't until Chandra's X-ray vision peeled back the layers of debris that the truth emerged. A neutron star was there all along, glowing quietly in X-rays while remaining radio silent. What makes objects like this so elusive isn't just their lack of radio emissions, it's the subtlety of their X-ray signatures. Unlike the searing beams of an active pulsar, these neutron stars emit thermal X-rays, the residual heat from their unimaginably dense cores bleeding through their surfaces. Cassiopeia A's neutron star, for instance, radiates at around 2 million degrees Celsius, scorching by human standards, but a faint flicker compared to the high-energy fury of younger, magnetically powered pulsars. Spotting these dim embers requires painstaking analysis, teasing their weak signals from the noisy X-ray glow of surrounding supernova debris. The silence speaks volumes. A neutron star's radio beams depend on a precise alignment of magnetic poles and rotation axis, like a lighthouse whose light only reaches observers in a narrow corridor. If those beams don't sweep across Earth, we'll never detect the radio pulses, no matter how powerful they are. But thermal X-rays, they radiate in all directions, offering a fail-safe way to detect neutron stars that would otherwise stay hidden. Cassiopeia A's resident isn't alone in its quietude. The neutron star at the heart of the supernova remnant G300.2-2.9 similarly lacks radio pulses, yet its X-ray glow confirms its presence. Some of these silent stars might be young, their magnetic fields not yet settled into the organized structures needed to generate coherent radio beams. Others could be old, their once fierce emissions faded to near nothingness after millennia of energy loss. But the real intrigue lies in the outliers, neutron stars that should be blaring radio signals but stubbornly refuse. One theory suggests their magnetic fields are tangled into complex knots, disrupting the formation of clean polar beams. Another proposes that dense debris from their birth supernova might absorb radio waves before they escape, like fog swallowing a lighthouse's glow. These X-ray whispers are cosmic breadcrumbs, leading us to a startling realization. For every bright pulsar we've catalogued, there might be dozens of silent ones lurking unseen. Their very existence challenges assumptions about how neutron stars form, evolve, and interact with their environments. And with every new detection, we're forced to ask, how many more are out there, quietly waiting for us to listen in the right wavelength? Beneath the crushing density of a neutron star's iron crust, an ocean of pure strangeness churns, a frictionless quantum fluid unlike anything found on Earth. This isn't just exotic matter, it's a superfluid, a state where neutrons, freed from the shackles of viscosity, flow with impossible perfection. Imagine a whirlpool spinning forever without slowing, or ice melting the moment you touch it. Only here, the rules of quantum mechanics rewrite reality at scales larger than a city. The evidence for neutron star superfluidity comes from their bizarre spin behavior. When a pulsar suddenly speeds up in a glitch, it's not just the crust cracking, it's the superfluid beneath the surface finally catching up. Here's how it works. As the star's rotation gradually slows over centuries, its superfluid core, utterly unaffected by friction, keeps spinning at its original pace. The difference builds until snap vortices in the superfluid suddenly transfer their pent-up momentum to the crust, kicking the star's rotation faster in milliseconds. It's like a figure skater's hidden partner, invisible but capable of yanking them into a sudden pirouette. But this quantum ballet gets even weirder. In labs on Earth, superfluids like liquid helium exhibit mind-bending properties, climbing walls, slipping through microscopic cracks, even defying gravity. Now scale that up to a neutron star's interior, where the superfluid isn't chilled helium but a sea of neutrons packed tighter than atoms in a diamond. Simulations suggest this neutron soup might form intricate vortex lattices spinning whirlpools thinner than a human hair but stretching miles long, each one carrying a tiny fraction of the star's angular momentum. When these vortices unpin from the crust's underside, the resulting energy transfer can trigger glitches or even starquakes. The real shocker, some theories propose the superfluid doesn't stop at neutrons. Deeper still, pressures might crush neutrons themselves into quarks, creating a quark-gluon plasma with its own superfluid properties, a cosmic matryoshka doll of quantum oddities. This could explain why some neutron stars, like Vela, glitch predictably every few years while others erupt chaotically. The superfluid's depth, temperature, and composition might dictate the rhythm of these cosmic hiccups. Yet for all its strangeness, this phenomenon isn't just theoretical. Observations of cooling neutron stars like Cassiopeia A's remnant show temperature drops that match superfluid models, as if something beneath the surface suddenly switched on, accelerating heat loss like a radiator cranked to maximum. It's a ghostly fingerprint of quantum physics playing out on a stellar scale, proving that even in the coldest corners of space, the universe never stops surprising us. The takeaway: neutron stars aren't just dead stars, they're quantum laboratories, their cores hosting physics so extreme it defies earthly intuition. Every glitch, every temperature flicker is a message from a realm where matter forgets its ordinary rules. And the only certainty is that we've barely scratched the surface of its secrets. Not every cosmic lighthouse announces itself with radio waves. Some shine only in the most lethal light on the spectrum. Lurking in the shadows of traditional pulsar surveys, these ghostly neutron stars reveal themselves solely through gamma rays, the highest energy photons in the universe. NASA's Fermi Gamma Ray Space Telescope revolutionized our understanding of these phantoms when it began scanning the skies in 2008, uncovering an entire population of pulsars that radio telescopes had missed for decades. These aren't just dim versions of ordinary pulsars, they're cosmic chameleons. They're beams of radiation tuned to frequencies too extreme for most instruments to detect. Take PSR J035 7+3205, one of Fermi's earliest and most baffling discoveries. This pulsar spins 316 times per second, whipping its gamma-ray beams across space like a hyperactive strobe light. Yet point a radio telescope in its direction, and you'd hear nothing but silence. The reason lies in the star's magnetic geometry. Unlike traditional pulsars, where radio waves emanate from low-altitude magnetic poles, gamma-ray pulsars likely produce their radiation much farther out in the magnetosphere, where particle acceleration reaches energies capable of generating gamma photons. It's the difference between a flashlight's gentle glow and the searing beam of a particle accelerator. What makes these objects so valuable isn't just their invisibility to radio, it's the clues they hold about pulsar diversity. Fermi's census revealed that gamma-ray-only pulsars outnumber their radio-loud counterparts in some regions of the galaxy, suggesting we've been missing a significant fraction of the neutron star population all along. Some, like the enigmatic Geminga, are so quiet in other wavelengths that they were mistaken for ordinary gamma-ray sources for years before their pulsations gave them away. Others, like Pulsar J100, 1-5923, flicker so erratically in gamma rays that their pulse timing resembles a sputtering engine rather than a metronome. The key to their stealth: beam width. Gamma-ray emission appears to be broader than radio beams, meaning these pulsars don't need perfect alignment with Earth to be detected. A radio pulsar's narrow beam might sweep past us unnoticed, while its gamma-ray counterpart still floods our telescopes with photons. This explains why Fermi's all-sky surveys uncovered pulsars in regions radio astronomers had previously written off as empty. But the real puzzle is how these stars generate such focused gamma rays in the first place. Current theories point to outer gap acceleration regions high above the neutron star's surface, where magnetic field lines twist into knots, creating natural particle colliders. Electrons trapped in these gaps spiral along the field lines at near light speed, emitting gamma photons through a process called curvature radiation. Other models suggest the gamma rays might arise from cascades of electron-positron pairs crashing into the star's magnetosphere, like cosmic fireworks ignited by colliding shockwaves. The implications stretch far beyond cataloging exotic pulsars. These gamma-ray phantoms are natural probes of interstellar space, their high-energy photons slicing through dust clouds that would absorb lower-energy radiation. By mapping how their signals dim or scatter, astronomers can trace the Milky Way's hidden gas reservoirs, the very material that births new stars. And because gamma rays aren't easily distorted by interstellar plasma, they offer cleaner measurements of pulsar distances than radio waves ever could. Perhaps most tantalizing is what these ghosts imply about the limits of discovery. If neutron stars can hide in plain sight by masking their radio voices, what else might Fermi or its successors unearth? Every flicker in the gamma-ray fog is a reminder that the universe still holds cards close to its chest, waiting for us to look with the right eyes. And as Fermi's mission continues, who knows how many more of these silent but deadly lighthouses are waiting to step into the light. Imagine a lighthouse that doesn't just blink, it disappears entirely for minutes at a time, as if someone flipped a cosmic switch. That's exactly what happens with PSRB 1957+20, a neutron star locked in such a tight orbit with its stellar companion that the smaller star periodically blocks its pulses from Earth's view. Astronomers call these events pulsar eclipses, but they're less like the orderly shadow play of a solar eclipse and more like a chaotic cosmic game of peekaboo where the rules keep changing. What makes these eclipses so bizarre is the sheer violence of the environment. The companion star isn't just passively blocking light, it's being actively devoured. As the pulsar's relentless radiation strips gas from its partner, the stolen material forms a swirling, ionized shroud around both stars. When this shroud passes between the pulsar and Earth, it doesn't merely dim the pulses, it smothers them completely, swallowing radio waves like a black hole swallowing light. The eclipse isn't a clean shadow. It's a turbulent fog with patches of dense plasma extinguishing the signal for up to 15 minutes at a time before suddenly clearing like storm clouds parting. The dynamics here defy intuition. Unlike a planet eclipsing a star where the transition is sharp and predictable, pulsar eclipses flicker erratically. Observations of PSRB 1957 plus 20 reveal pulses cutting out mid-beat as if the neutron star is being drowned in real time. This happens because the eclipsing material isn't static. It's a churning, magnetized maelstrom with clumps of gas 10 times denser than the surrounding wind. Radio waves trying to pierce this chaos scatter wildly, their signals scrambled beyond recognition, yet these eclipses are gold mines for scientists. By analyzing how the pulsar's signal distorts as it passes through the companion's atmosphere, astronomers can map the gas stream structure with kilometer-scale precision. It's like cosmic tomography, using the pulsar's beams as X-rays to probe the invisible. Some studies have even caught the eclipses changing shape over months, evidence that the companion star's atmosphere is being reshaped by the pulsar's fury, its outer layers boiling away into asymmetrical plumes. The most haunting detail, these eclipses are temporary. As the pulsar keeps consuming its partner, the eclipses will grow shorter and fainter until, one day, they stop altogether. The companion star will be gone, and the pulsar's pulses will shine unobstructed, a lonely beacon in the dark, its violent dance finally ended. Until then, every disappearance is a reminder of how dynamic, how utterly unpredictable the universe can be, even in something as seemingly simple as a flickering light. Most neutron stars blaze with the heat of their violent births, but what happens when even that fire fades? Billions of years from now, long after their pulsar beams have dimmed and their X-ray glows have cooled to black, the universe's oldest neutron stars will slip into darkness as silent relics of a forgotten era. These cosmic embers, having radiated away their last traces of thermal energy, would become virtually undetectable unless you knew exactly where and how to look. The hunt for these ghostly, relic neutron stars is rewriting the rules of stellar archaeology. Unlike their younger counterparts, which scream their presence across the electromagnetic spectrum, ancient neutron stars might only betray themselves through the faintest infrared glow, a whisper of residual warmth clinging to their surfaces after eons of cooling. NASA's upcoming Nancy Grace Roman Space Telescope, with its unprecedented infrared sensitivity, could finally spot these elusive fossils by detecting their thermal signatures against the cold backdrop of interstellar space. Imagine scanning the sky for something colder than most planets, dimmer than distant asteroids, yet denser than anything else in the galaxy. The challenge isn't just technological, it's theoretical. Models suggest the oldest neutron stars could have surface temperatures below 1000 Kelvin, colder than a campfire. Their composition might determine whether they fade evenly or develop bizarre cold spots where heat bleeds away faster. Some could even be cloaked in thick atmospheres of hydrogen or carbon, acting like cosmic insulation that slows their cooling to a crawl. Others, stripped bare by magnetospheric winds, might freeze faster, their smooth surfaces radiating heat into the void like perfect blackbodies. What makes these relics especially tantalizing is what they could reveal about the early universe. The oldest neutron stars would have formed when galaxies were young, potentially carrying imprints of primordial conditions in their crustal chemistry or magnetic field decay. Finding one floating alone in intergalactic space, a refugee from a galaxy long since merged or dispersed, would be like discovering a perfectly preserved fossil from the cosmic dark ages. Yet the ultimate prize would be locating a relic that shouldn't exist, a neutron star older than the universe itself appears to allow. Current cooling models suggest none should have reached absolute zero yet, but if telescopes found one that's inexplicably cold, it might hint at exotic physics at play, perhaps dark matter interactions sapping their heat, or undiscovered particles carrying energy away faster than predicted. The search plays out like cosmic forensics. Astronomers comb through infrared surveys for unexplained point sources moving too fast to be planets, too cold to be white dwarfs. Some candidates, like the mysterious object X in the Andromeda Galaxy's halo, have already sparked debates. Could this dim, wandering speck be the first identified relic? Every unaccounted for neutron star represents a missing piece in the life cycle of stellar remnants. If too many relics evade detection, it might mean they cool differently than we think, or that some have already crossed into a new phase of existence, their matter crystallizing into quantum oddities we've yet to imagine. The universe has a way of hiding its oldest secrets in plain sight, waiting for the right tools and the right curious minds to tease them from the dark. The next time two neutron stars collide in the darkness of deep space, they won't just send ripples through space-time, they'll send echoes. Gravitational waves from these mergers already revolutionize astronomy, but future detectors like the Laser Interferometer Space Antenna LISA and the Einstein telescope promise to catch something even more extraordinary: the faint, stretched-out reflections of ultra-distant collisions arriving years after the original event. These delayed signals won't just confirm a merger happened, they'll act as cosmic tape measures, revealing how fast the universe itself is stretching over incomprehensible distances. Here's how it works. When gravitational waves from a neutron star merger traverse the expanding cosmos, they don't just travel in a straight line. Dense galaxy clusters and dark matter halos warp their path, bending some waves onto longer trajectories. The result, a single cataclysm could produce multiple arrivals at Earth, the initial burst followed by ghostly echoes delayed by months or even years. It's like shouting across a canyon and counting the seconds between your voice and its rebound, except here, the canyon is the universe and the echoes carry clues about everything they've passed through. The real power of these gravitational echoes lies in their distortion. As space expands, it stretches the wavelengths of the waves, shifting them toward lower frequencies. By comparing the original merger signal with its delayed counterparts, astronomers could measure this stretching with unprecedented precision, calculating the universe's expansion rate, the Hubble constant, without relying on traditional methods like supernova or cosmic microwave background radiation. This is critical because current measurements disagree wildly, a discrepancy dubbed the Hubble tension that might hint at undiscovered physics. Gravitational echoes offer a third, independent way to resolve the conflict, using spacetime itself as the ruler. The most tantalizing targets, mergers so distant their light will never reach us. Gravitational waves don't dim like photons, they pierce through dust, gas, and even entire galaxies unscathed. A collision 12 billion light-years away, from an era when the universe was a fraction of its current size, might be invisible to telescopes but crystal clear to LISA million-kilometer-wide antenna. Its echoes could reveal how expansion accelerated during cosmic epochs we've only glimpsed indirectly, filling gaps in our timeline of the universe's evolution. Yet catching these echoes demands patience and luck. The timing between signals depends on the exact distribution of dark matter and galaxies along the wave's path, structures we're still mapping. Some models suggest rare caustic echoes where waves bend around massive objects like black holes could arrive amplified, ringing louder than the original merger. Others predict faint, scrambled versions requiring AI-driven pattern recognition to untangle from background noise. But if we succeed, the payoff is staggering. Each echo would encode a snapshot of cosmic expansion at a specific moment in history, letting us reconstruct how dark energy's influence has changed over billions of years. It's like finding a stack of cosmic postcards, each stamped with the universe's growth rate at a different epoch, and together they might just reveal what's really driving the cosmos apart. Einstein would have loved PSR J0737-3039, a cosmic dance so precise it bends the rules of reality itself. This isn't just any binary system. It's a pair of neutron stars locked in a gravitational tango so tight they orbit each other faster than a bullet's flight, completing a full loop every 2.4 hours. But here's where relativity steps in. The pulsar closer to Earth isn't just a silent partner. It eclipses its twin every 22 minutes, blotting out its radio pulses like a cosmic hand flicking a switch. This isn't a simple shadow play, it's a laboratory for testing spacetime itself. The eclipses reveal secrets no solo pulsar could. As the foreground star passes in front of its twin, its gravity warps the path of the background pulsar's radio beams, bending them around its bulk like light through a lens. The timing of these blackouts isn't random, it follows Einstein's playbook to the millisecond, proving that even in the vacuum of space, mass curves the fabric of reality. But the real magic happens when the eclipsing star's magnetosphere, a turbulent zone of charged particles, scrambles the hidden pulsar's signal. By analyzing how the radio waves distort, astronomers can map the invisible magnetic storms raging between them, a feat like diagnosing a hurricane by listening to static on a distant radio station. Yet the true test of relativity lies in their orbital decay. These stars spiral inward at the exact rate Einstein predicted, losing energy as gravitational waves ripple outward, a slow-motion collision that'll culminate in a kilonova explosion 300 million years from now. Every eclipse, every tick of their orbital clock is a victory for general relativity, proving that even in the most extreme corners of the universe, the rules hold firm. But PSR J0737-3039 isn't just confirming what we know, it's pushing boundaries. Tiny discrepancies in its timing could hint at physics beyond Einstein, perhaps even whispers of quantum gravity or extra dimensions. For now, this binary remains a cosmic metronome, its eclipses ticking off the seconds until the next revolution in physics. And when that day comes, the universe's most precise clocks might just reveal the cracks in our understanding or cement Einstein's legacy for another century. Stretching across light years like cosmic blowtorches, the supersonic winds of neutron stars don't just fade into the void, they sculpt. When these stellar remnants unleash their relativistic jets and particle storms, they don't merely pass through interstellar gas, they remodel it, carving out cavernous bubbles that linger for millennia. Telescopes like the Very Large Array have caught these structures in stunning detail, hollows of glowing plasma where the neutron star's fury has shoved aside entire clouds of molecular hydrogen, leaving behind shock fronts that ripple outward at millions of miles per hour. Take the mushroom cloud in the constellation Cygnus, a 10-light-year-wide cavity blown clean by the pulsar B0750-36. Radio images reveal its walls shimmering with synchrotron radiation, evidence of electrons spiraling along magnetic field lines at nearly light speed. What's astonishing isn't just the scale, but the violence of its creation. The pulsar's wind slams into surrounding gas like a fire hose against smoke, heating it to tens of millions of degrees and ionizing atoms so thoroughly they emit radio waves like cosmic neon signs. Over centuries, this relentless pressure inflates the bubble further, its edges sharp as crystal against the softer glow of undisturbed space. But the real marvel lies in the physics of these shock fronts. As the neutron star's wind collides with interstellar gas, it doesn't just push, it transforms. Particles accelerated at the boundary generate cascades of secondary radiation, from radio waves to gamma rays, painting the bubble's surface in multicolor fury. Some of these structures, like the one surrounding the Geminga pulsar, even exhibit reverse shocks, regions where interstellar pressure fights back, compressing the wind into intricate filaments that glitter in X-ray observations. It's a standing testament to balance, the neutron star's outrage against the quiet resistance of the galaxy itself. These bubbles aren't just celestial artwork, they're fossil records. By measuring their size and the energy required to create them, astronomers can reconstruct the neutron star's history. The pistol star's surrounding cavity, for instance, suggests its pulsar once unleashed a wind 1,000 times more powerful than today, a relic of its youth when it spun faster and burned brighter. Others, like the faint shell around PSRJ 0622 plus 3749, tell darker tales. Their lopsided shapes hint at turbulent interstellar environments or violent encounters with passing stars. Perhaps the most profound implication is how these shockwaves seed future star formation. As they expand, they sweep up surrounding gas into dense shells, cosmic snowplows piling up interstellar snow. Eventually, these compressed regions might collapse under their own gravity, igniting new stars in the neutron star's wake. In a twist of stellar irony, the death shudders of one star become the birth cries of others, threading the galaxy's life cycle across generations. So next time you see a radio map streaked with glowing voids, remember, you're not just looking at empty space, you're witnessing the aftermath of a neutron star's rage, a testament to how even the smallest objects can leave the largest marks on the cosmos. Some neutron stars aren't content with silently spinning their cosmic vampires, feasting on their stellar companions in a slow-motion act of celestial cannibalism. These aren't the polite diners of the galaxy. Systems like SAX-J1 808.4-3658 erupt in violent thermonuclear explosions every few hours as stolen stellar material detonates on the neutron star's surface. Imagine a teaspoon of gas ripped from a neighboring star, compressed to unimaginable densities, then ignited in a blast equivalent to 100 million hydrogen bombs, all happening on a loop like clockwork. This vampiric process starts with gravity's relentless pull. The neutron star's immense density creates a gravitational well so steep, it peels away layers of its companion's outer atmosphere like an apple being skinned. But here's where things get explosive. The stolen gas doesn't land gently. Accelerated to nearly half the speed of light, the plasma slams into the neutron star's surface with such force, it triggers runaway fusion in a process called a Type I X-ray burst. Telescopes have captured these eruptions in real time, a sudden spike in X-ray brightness that can outshine an entire galaxy for 10 terrifying seconds before fading away. What makes these bursts so valuable to scientists isn't just their violence, it's their precision. Unlike supernova that happen once, these thermonuclear flashes recur like cosmic metronomes, some every few hours, others on monthly cycles. Each burst acts like an X-ray fingerprint, revealing the composition of the stolen material. The light spectrum might show traces of helium, carbon, or even heavier elements, telling astronomers exactly what elements are being forged in these raging stellar kitchens. The most extreme vampire pulsars take this feast to horrifying extremes. In systems like IGRJ 17911-2502, the neutron star's magnetic field channels the stolen gas into columns that strike the surface with the energy of a particle accelerator, creating focused hotspots that reach 100 million degrees. Others, like Swift J1 749.4-2807, exhibit superbursts, rare, catastrophic detonations where accumulated carbon layers ignite simultaneously, releasing more energy in an hour than our sun does in a decade. But the real tragedy plays out on the donor stars. Over centuries, these companions are methodically drained, their outer layers stripped until only a shriveled core remains. Hubble has caught these victims mid-disassembly, stars stretched into teardrop shapes by their neutron star partners' gravity, their surfaces boiling away into space like steam from a kettle. Some, like the infamous Black Widow pulsar, have already reduced their companions to planetary mass husks, leaving behind a trail of ionized gas that glows faintly in telescope images like the aftermath of a cosmic crime scene. Yet for all their destructive power, these vampiric systems are teaching us how elements spread through the galaxy. Every thermonuclear burst seeds space with freshly minted atoms, carbon, oxygen, even traces of gold blasted outward by the explosion's force. It's a sobering thought. The very atoms that make up our bodies might have once been hurled into the void by the death throes of a star being eaten alive. The universe, it seems, recycles tragedy into creation, one stolen breath of stellar gas at a time. Peeling back the layers of a neutron star's surface is like cracking open a cosmic time capsule, one that's been sealed since the violent moment of its birth. These stellar remnants don't just carry the scars of their supernova explosions. They're studded with elemental fingerprints from those cataclysms, preserving a snapshot of the universe's most extreme alchemy. Imagine a forge so hot it fuses atoms in seconds, then freezes them in place for billions of years. That's the surface of a neutron star, where traces of titanium, chromium, and even gold linger like ashes from a primordial fire. Take the neutron star at the heart of the Cassiopeia, a supernova remnant. X-ray telescopes have detected strange, bright spots on its surface, concentrations of titanium and chromium that shouldn't exist if the star had formed evenly. The likely explanation: these metals were forged in the supernova's shockwave, then hurled backward like cosmic shrapnel to embed themselves in the neutron star's crust as it cooled. It's as if the explosion's final act was to tattoo its own debris onto the survivor's skin. But the real forensic goldmine lies in lighter elements like carbon and oxygen. When a massive star collapses, its outer layers rich in these lighter atoms get blasted outward at hypersonic speeds. Most escapes into space, but some rains back down onto the newborn neutron star, forming a thin atmospheric veneer. The European Space Agency's XMM Newton telescope has spotted neutron stars with oxygen-dominated atmospheres, their spectral lines betraying the composition of the original star's outer shells. Others, like the exotic object RxJ0852-46222, show evidence of carbon, snow, crystallized patches where carbon from the supernova fallout condensed like frost on a windowpane. The most astonishing preservation happens deeper down. Neutron star crusts are layered like onions, with heavier elements like iron sinking beneath lighter ones. Simulations suggest these strata might hold isotopes like nickel-60, a radioactive tracer that only forms in supernova-like tree rings recording the explosion's intensity. Some theorists even speculate that rare earth elements like neodymium could accumulate in cosmic reefs just below the surface, their presence detectable through subtle distortions in the star's X-ray glow. What makes these stellar fossils so valuable isn't just their age, it's their purity. On Earth, geological processes constantly recycle and mix elements, erasing primordial clues. But a neutron star's surface is a sterile vault. With no weather, no tectonics, and gravity 100 billion times stronger than Earth's, its elemental graffiti stays untouched for epochs. Every atom is a witness waiting for us to decode its story, one X-ray photon at a time. And here's the kicker: some of these elements might be ones we've never seen before. The supernova's neutron-rich environment could have forged ultra-heavy isotopes that decayed instantly under normal conditions, but remain frozen in the neutron star's crushing grip. Finding them would be like uncovering a lost chapter in the periodic table, one written in the language of dying stars. So next time you hear about a neutron star's spin or magnetic field, remember beneath all that fury lies a museum. Its exhibits are atoms, its curator is gravity, and its collection stretches back to the beginning of time itself. Fast radio bursts, those mysterious millisecond-long blasts of cosmic static, have puzzled astronomers since their discovery in 2007. These eruptions pack as much energy as 500 million suns, yet vanish almost instantly, leaving behind more questions than clues. But in April 2020, something extraordinary happened. A magnetar named SGR 1935+2154, located 30,000 light-years away in our own galaxy, fired off a burst that cracked the case wide open. For the first time, telescopes caught a fast radio burst in action, tracing it directly to one of the universe's most volatile objects, a neutron star with a magnetic field strong enough to warp atoms. The connection wasn't just a lucky coincidence. This magnetar had been restless for weeks, erupting with smaller X-ray flares before unleashing its record-breaking radio burst. When the signal reached Earth, it was captured simultaneously by the Canadian Hydrogen Intensity Mapping Experiment and NASA Neil Gehrels Swift Observatory, a 1-2 punch of radio and X-ray data that left no doubt about the source. The implications were staggering. At least some fast radio bursts weren't alien signals or exotic physics, but the death screams of magnetars in the throes of starquakes or magnetic upheavals. Yet the story isn't that simple. While SGR 1935 plus 2154's burst matched the profile of some extragalactic fast radio bursts, it was thousands of times weaker than the most powerful events detected from distant galaxies. This raises a tantalizing question. Are magnetars behind all fast radio bursts or just a subset? The repeating bursts, those that flicker on and off like cosmic strobe lights, seem the likeliest candidates. Their erratic cadence mirrors the unpredictable outbursts of magnetars, suggesting a shared engine of destruction, the snap and recoil of magnetic field lines near the neutron star's surface. One of the most infamous repeaters, FRB 1211 plus 2021, adds fuel to the debate. Located 3 billion light-years away, this source flares multiple times an hour, its bursts varying wildly in brightness. Some theorists argue this behavior points to a hypermagnetized neutron star periodically cracking under stress, its crust fracturing like ice sheets in an earthquake. Others propose even wilder explanations, collapsing asteroid belts or lightning storms in superheated plasma clouds trapped by the star's gravity. The magnetar hypothesis gained further traction in 2023 when the European Space Agency's integral satellite detected gamma-ray flares from another potential repeater, FRB 2255 plus 2536. These high-energy whispers align with what we'd expect if a magnetar's crust ruptured, sending shockwaves through its magnetosphere. But skeptics point out key differences. Extragalactic fast radio bursts often show signatures of passing through dense plasma, suggesting origins in star-forming regions or supernova remnants and environments where young magnetars thrive. Yet some repeaters, like FRB 1809016 plus 359, reside in oddly quiet galactic neighborhoods far from the stellar nurseries that birth neutron stars. What makes this detective work so thrilling is the sheer diversity of fast radio bursts. Some, like the Lorimer burst, are one-off events, cosmic lightning strikes with no encore. Others, like FRB 121122, erupt in predictable patterns, hinting at orbital influences or rotational cycles. Magnetars can explain some of these behaviors, but perhaps not all. The universe, it seems, has more than one way to manufacture these brilliant flashes, whether through magnetic mayhem, colliding neutron stars, or phenomena we've yet to imagine. For now, the hunt continues. Every new fast radio burst detected, especially those with galaxy-spanning echoes, adds another piece to the puzzle. And with telescopes like the Deep Synoptic Array in California scanning the skies daily, it's only a matter of time before another magnetar steps into the spotlight, either cementing its role as the prime suspect or forcing us to rethink the case entirely. One thing's certain, when it comes to fast radio bursts, the most exciting answers are still hanging in the static. Neutron stars might be the universe's ultimate dark matter detectors, cosmic traps so dense they could capture particles we've never seen. Picture this: dark matter, the invisible stuff making up 85% of the universe's mass, is thought to drift through space like a ghostly wind, barely interacting with ordinary matter. But a neutron star's gravity is no ordinary force. With a pull strong enough to bend light into a halo, these stellar corpses could act like galactic flypaper, snagging dark matter particles that pass too close and holding them in a gravitational vise. The math is compelling. A single neutron star's density creates a gravitational well so steep, even elusive dark matter particles, if they collide with atomic nuclei in the star's crust, could lose enough energy to become trapped. Over billions of years, these accumulated particles would sink to the core, annihilating or decaying in ways that inject extra heat into the star. This would slow its cooling rate, leaving ancient neutron stars noticeably warmer than standard models predict. It's like finding a cup of coffee that stays hot for decades, except here, the heat might be evidence of dark matter's fingerprints. Some of the coldest neutron stars already hint at this anomaly. Objects like PSR J021, 8 + 4 232, which should have cooled to near absolute zero after hundreds of millions of years, instead glow faintly in X-rays. One explanation: dark matter collisions are reheating them from within, like a hidden furnace banked with invisible fuel. Simulations suggest certain dark matter candidates, like weakly interacting massive particles, or WIMP, could pile up in neutron star cores until their density triggers a runaway annihilation chain, creating a thermal signature detectable by telescopes like Chandra or the upcoming Athena mission. But the implications go beyond temperature. If dark matter truly clusters in neutron stars, it could warp their structure. Some theories propose that enough accumulated dark matter might soften a neutron star's core, lowering the maximum mass it can support before collapsing into a black hole. This could explain why we've never found a neutron star heavier than about 2.2 solar masses. Dark matter might be secretly tipping the scales. The wildest possibility: neutron stars could transform dark matter. In the core's extreme pressure, captured particles might morph into new states of matter, like dark neutron stars nested inside ordinary ones. Or their presence might catalyze exotic nuclear reactions, producing elements or energy signatures we've never observed. It's a cosmic paradox. The darkest objects in the universe might be our brightest hope for illuminating the nature of dark matter. Yet the hunt isn't simple. Competing theories like superfluid neutrons or unaccounted for magnetic fields could also explain anomalous cooling. And not all neutron stars are ideal dark matter nets. Those in dense galactic regions where dark matter is abundant should show stronger heating effects than isolated ones. Future telescopes capable of measuring neutron star temperatures with pinpoint precision could settle the debate, turning these stellar relics into the universe's most sophisticated dark matter laboratories. Until then, every oddly warm neutron star is a mystery waiting to be unraveled, a reminder that the universe's darkest secrets might be hiding in plain sight, etched into the fading glow of a stellar corpse. The surface of a neutron star isn't just hard, it's a quantum-engineered labyrinth where iron atoms are squeezed into shapes that defy nature's ordinary rules. Imagine taking the Eiffel Tower's steel framework and crushing it into a sugar cube, but instead of crumpling, the metal reorganizes into an ultra-dense crystalline lattice where nuclei aren't neatly spaced spheres but distorted into bizarre, elongated forms by gravity's unrelenting grip. This isn't science fiction, it's the reality of a neutron star's crust, a layer of matter so compressed, it challenges everything we know about atomic structure. At these extreme densities, the electrons that normally orbit atomic nuclei are long gone, squeezed into the nuclei themselves during the star's collapse. What's left are naked iron nuclei packed shoulder to shoulder in a crystalline arrangement resembling a 3D honeycomb. But here's the twist: gravity doesn't just squish this lattice, it warps it. Simulations reveal that under pressures 100 billion times Earth's surface gravity, the nuclei deform into cigar-shaped blobs or even pancake-like disks, their protons and neutrons barely held together by the strong nuclear force. The resulting structure is less like a solid and more like a quantum foam, with nuclei stretched so thin they're on the verge of dissolving entirely. The real magic happens at the crust's lower depths. As you descend toward the neutron star's core, the pressure mounts until even these distorted nuclei can't hold their shape. They shatter into free neutrons and protons, creating a transitional layer physicists call nuclear pasta, not because it's edible, but because the matter organizes into strands and sheets resembling spaghetti or lasagna. This exotic phase exists only in neutron stars, where gravity and quantum forces duel to create structures that couldn't form anywhere else in the universe. What's even wilder is how this quantum crust behaves under stress. When a neutron star's rotation or magnetic field strains the lattice, it doesn't bend like earthly metals. It cracks catastrophically, triggering starquakes that release more energy than 1 billion atomic bombs. These fractures might even expose the nuclear pasta beneath, creating temporary volcanoes where superfluid neutrons erupt through the crust in violent geysers. Telescopes have caught X-ray flashes from events like these, brief but luminous flares hinting at the chaos churning just beneath the surface. Yet the crust's true value lies in its role as a cosmic laboratory. By studying how it vibrates during starquakes or responds to magnetic stresses, scientists can indirectly probe the star's interior, much like geologists use earthquakes to map Earth's core. The crust's thickness, estimated between 500 meters and 1 kilometer, holds clues about the neutron star's age, rotation, and even the nature of the mysterious quantum soup sloshing beneath it. Every glitch, every flare is a data point, helping unravel the physics of matter pushed beyond sanity's edge. And here's the kicker: this crystalline nightmare might be the most durable material in the universe. Laboratory experiments suggest neutron star crust is 10 billion times stronger than steel, so tough it could theoretically survive a direct impact from a small asteroid. But that durability comes at a cost. The crust's extreme density means a single cubic centimeter would weigh as much as a mountain on Earth, a reminder that even the universe's most unbreakable materials exist under conditions we can scarcely fathom. In the end, the neutron star's crust isn't just a curiosity, it's a boundary layer between the known and the unknown, where the familiar rules of matter break down and quantum weirdness takes over. Every vibration, every crack is a message from a realm where gravity and quantum mechanics collide, rewriting the textbook one atomic distortion at a time. Escaping a neutron star isn't just difficult, it's a battle against physics itself. Picture this: to break free from Earth's gravity, rockets need to reach 11 kilometers per second. But on a neutron star's surface, you'd need to hit 100,000 kilometers per second, nearly 1/3 the speed of light, just to have a chance. That's not merely fast, it's a velocity where Einstein's relativity becomes impossible to ignore, warping the very rules of motion we take for granted. At this insane speed, time and space behave differently. A clock on the neutron star's surface would tick noticeably slower than one in deep space, a phenomenon called gravitational time dilation. Even the concept of up gets twisted. Light emitted straight upward bends so severely that photons curve like baseballs lobbed through molasses. This isn't theoretical. Observations of neutron stars like PSRJ 0348+0432 show their gravity lensing background stars into Einstein rings, proving light itself struggles to climb free. The math behind this cosmic prison is staggering. A neutron star's escape velocity depends on its mass and mind-boggling compactness, typically just 12 miles wide yet weighing twice our Sun. This creates surface gravity 100 billion times Earth's, enough to squash atomic orbits into flat pancakes. Relativity equations reveal that at these extremes, Newton's simpler formulas fail spectacularly. What seems like a straightforward calculation, kinetic energy versus gravitational pull, becomes a dive into tensor calculus, where space-time curvature dictates whether anything, even light, can ever truly escape. What's truly humbling is how this warps our interstellar fantasies. Chemical rockets, useless, their exhaust couldn't reach a fraction of the required speed. Even antimatter engines, the stuff of sci-fi, would barely make headway. the only conceivable escape might involve riding a neutron star's own magnetic fury, harnessing its particle jets like a cosmic slingshot, but that'd require technology bordering on magic. Yet this extreme gravity isn't just a barrier, it's a tool. Astronomers use neutron star lensing to measure cosmic distances with precision, and their distorted light teaches us how matter bends the universe's fabric. Every photon that barely escapes carries data about conditions no lab could recreate. So while we'll never stand on their surfaces, these stellar fortresses still speak to us in the warped starlight they twist and the impossible challenges they pose to physics itself. The universe's most extreme physics labs won't stay mysterious for long. Cutting-edge missions are gearing up to crack neutron stars wide open. Leading the charge is NAS, a Neutron Star Interior Composition Explorer, or NICER, an X-ray telescope mounted on the International Space Station that's already rewriting the rulebook. Unlike conventional observatories, NICER operates like a cosmic CT scanner, measuring the precise timing of X-ray pulses to map the interior structure of neutron stars with unprecedented detail. Its crown jewel, pinpointing the equation of state, the fundamental relationship between a neutron star's mass and radius, which could finally reveal whether their cores harbor exotic quark matter or undiscovered particles. Recent data from Pulsar J0030+0451 showed surface hotspots where temperatures vary by millions of degrees, hinting at turbulent magnetic fields churning beneath the crust like subterranean storms. But the real game-changer lurks on the horizon, the Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s. This trio of spacecraft will form a 1 million-kilometer-wide gravitational wave detector in solar orbit, sensitive to ripples in spacetime from neutron star mergers up to 10 billion light-years away. While ground-based observatories like LIGO have caught fleeting merger signals, LISA revolutionary design will detect these collisions months before they happen by tracking the in-spiral of orbiting pairs with pinpoint precision. Imagine getting a front-row seat as two neutron stars spiral toward catastrophe, their gravitational waves shifting in pitch like a cosmic Doppler effect before the final, universe-shaking crescendo. This advance warning will let telescopes worldwide train their sights on the fireworks in real time, capturing everything from gamma rays to radio waves across the electromagnetic spectrum. Meanwhile, Europe's Athena X-ray Observatory, slated for 2033, will peer deeper into neutron star magnetospheres than ever before. Its advanced spectrometer can dissect the chemical makeup of their atmospheres atom by atom, potentially spotting rare elements forged during supernova or even dark matter particles trapped in their gravity wells. Athena's resolution is so sharp, it could detect mountains on neutron star surfaces, minuscule deformations less than a millimeter tall, warped by magnetic fields strong enough to twist spacetime itself. The most tantalizing possibilities lie in combining these missions. NICER interior maps, LISA gravitational soundtracks, and Athena's surface scans could together construct the first 3D portrait of a neutron star from crust to core. Will we find proof of hyperfluid neutrons swirling beneath the surface, or catch a quark-gluon plasma in the act of crystallization? The answers might rewrite textbooks or unveil phenomena so bizarre they demand entirely new physics. One thing's certain, the golden age of neutron star science isn't on the horizon. It's already here. From the mind-bending density of neutron stars, where a single teaspoon weighs as much as a mountain, to the real-life vampires feasting on their stellar companions, these cosmic oddities have shattered every expectation. We've uncovered stars spinning faster than kitchen blenders, magnetic fields strong enough to distort atoms from light years away, and collisions so violent they forge gold in cosmic kilns. Yet for every mystery solved, a dozen more remain. What lurks in the quantum depths of their cores? Free-floating quarks, exotic particles, or something beyond our wildest theories? Why do some pulsars suddenly switch personalities, flipping between radio whispers and gamma-ray screams? And how many silent neutron stars drift unseen, cloaked in darkness between the stars? The deeper we look, the stranger it gets. Take the chameleon pulsar, defying logic by vanishing and reappearing like a cosmic ghost, or the runaway neutron stars hurtling through the void at millions of miles per hour, exiled from their birthplaces by supernova gone rogue. Even the echoes of ancient stellar deaths like the Crab Nebula's heartbeat, synchronized with records from 1,000 years ago, remind us that these objects are more than scientific curiosities. They're time capsules carrying secrets from the universe's most violent moments. So which fact left you reeling? Was it the Starquakes cracking crust stronger than steel, the nuclear volcanoes spewing superfluid nightmares, or the light-bending gravity warping space-time itself? Drop your favorite in the comments. I'd love to hear which cosmic absurdity blew your mind the most. And if you're hungry for more interstellar mysteries, hit subscribe. The universe is brimming with enigmas, and we're just getting started. Until next time, keep looking up, because out there the rules are